Carrier 257, hold north of Gill VOR on the 350-degree radial. Left turns 8,000.
Crusader 32 Charlie, cleared to land runway 29er right, wind 310 what's up.
King Air 17 Hotel, cleared to the Evergreen Airport, Victor 15, that is filed. Maintain 7,000, departure control frequency 1.
Mooney 43 Echo, turn right, heading 240, descend and maintain.
Seneca 9150 Zulu, maintain VFR conditions above 11,000.
Falcon 29er Echo, cleared to land runway 35 right, wind 3405, caution wake turbulence.
During your private pilot training, your flight instructor gave you the opportunity to control the airplane by instrument reference for brief periods of time. As you enter the world of instrument flight, you need to develop the knowledge and skills to fly the airplane on a continuous basis by referring solely to your instruments and gauges. When you enter the IFR environment, it's essential to know how the instruments work and to understand their limitations so you can properly interpret the information they display. To begin, let's review the basic flight instrument systems. You should remember from your private pilot training that the flight instruments are divided into two systems, gyroscopic or pedostatic. The gyro instruments include the attitude indicator, heading indicator, and turn coordinator, while the pedostatic instruments are the airspeed indicator, the altimeter, and the vertical speed indicator. Let's look closely at the gyro instruments. On most small airplanes, the gyros in the attitude indicator and heading indicator are vacuum driven, while the turn coordinator is electrically powered. By having different power sources for the individual gyros, you'll have backup information if one system fails. One of the main reasons a gyroscopic instrument is able to display its information is because of a principle called rigidity in space. Inside the instrument, a rapidly spinning gyro tends to resist the external forces produced as the airplane maneuvers around it. By having the gyro remain in a relatively fixed position, the aircraft's attitude can be measured in relation to the gyro. The turn coordinator also incorporates another principle called precession. Whenever your airplane's attitude changes, the pressures exerted by the external forces tend to make the gyros change their plane of rotation, or precess. The faster the change, the greater the pressures, and therefore the precession. The turn coordinator measures the precession of its gyro and indicates the rate of turn. However, precession is not always beneficial and can cause errors, which we'll discuss later. During VFR flight, you were able to maintain the aircraft's attitude by comparing references on the airplane to the natural horizon. During instrument flight, you no longer have that luxury. Now you must rely on the flight instruments for pitch and bank information. The one instrument which directly shows both pitch and bank is the attitude indicator. However, because of precession, the attitude indicator could give you erroneous indications. For example, if you accelerate rapidly, the instrument may indicate a slight climb. If your reaction is to lower the nose to return the miniature airplane back to level, your actual pitch attitude will be lower than that shown on the instrument. This will place your airplane in a descent unless you take corrective action. The opposite occurs when you decelerate rapidly. Here, the initial indication is that of a slight descent. Now let's review the heading indicator. The spinning gyro in the heading indicator is aligned with the vertical plane, allowing it to sense any changes in the airplane's vertical axis. The heading indicator is very susceptible to gyroscopic precession. As you maneuver the airplane, the external forces acting on the gyro cause the heading to drift very slowly. In this case, it is drifted 5 degrees. For this reason, you need to periodically realign it with the magnetic compass. Because the operation of the attitude and heading indicators relies on vacuum pressure, be sure to include the vacuum indications in your scan. The third gyroscopic instrument is the electrically powered turn coordinator. Although the miniature airplane looks like it is banking, it is only measuring the rate of turn or roll rate. It does not show angle of bank or pitch information. One of the most important uses of the turn coordinator is that it enables you to establish and maintain a standard rate turn, which is the rate you should use for most instrument maneuvers. With the wings of the miniature airplane aligned with the reference mark, you'll turn at a rate of 3 degrees per second. The second part of the turn coordinator is the inclinometer. Just as in VFR flight, the ball helps you maintain coordinated flight. Now let's re-examine the pitot-static instruments and look at their importance during your transition to the IFR environment. The basis for the functioning of the pitot-static instruments is differential air pressure. While the air pressure surrounding the airplane is vented to all three through a static port, only the airspeed indicator receives ram air pressure. This instrument measures the difference between the ram air and static air pressure and displays the result as an indicated airspeed. Knowing your relationship to terrain and obstructions would be virtually impossible at various times during your instrument flight without the information provided by the altimeter. As you learned during your private pilot training, the altimeter senses changes in the surrounding air pressure. Your mean sea level altitude is shown when you adjust the instrument to the correct local altimeter setting. If you didn't adjust your altimeter to the changing conditions, your actual height above sea level would be higher or lower than that indicated. Remember that as atmospheric pressure increases, your actual altitude is higher than that indicated. When the pressure decreases, your actual altitude is lower than indicated on the altimeter. To prevent the wrong indication, you should set your altimeter to the local altimeter setting. During instrument flight, air traffic control periodically provides you with the correct altimeter setting. The final pitot-static instrument is the vertical speed indicator. Although it is not required for instrument flight, you'll find that it's extremely useful for helping to control the airplane precisely in instrument weather. The VSI senses how fast the surrounding air pressure decreases or increases as you climb or descend, and displays the change as a rate in feet per minute. When a change in altitude occurs, the VSI immediately registers the trend of movement. It then stabilizes to show the actual rate. As an instrument pilot, you should be aware of the erroneous readings which can occur if the pitot-static system becomes blocked by ice, dirt, or even insects. If the pitot tube becomes blocked, two types of errors can occur with the airspeed indicator. If the air inlet is blocked but not the drain hole, the pressure in the line will vent out the opening, causing the indicator to drop to zero. However, if both openings are clogged while the static port remains open, air pressure remains in the line and the airspeed indicator now performs like the altimeter. As the airplane climbs from the altitude where the blockage occurred, the airspeed increases. Conversely, as you descend, the airspeed decreases. To help prevent blockages in the pitot system when operating in possible icing conditions, you should make sure the pitot heat is on if your airplane is so equipped. If the pitot tube remains open but the static system becomes blocked, the airspeed indicator still reacts to changes in airspeed. However, the indications are not correct. If you're operating at a higher altitude than where the system became blocked, then the airspeed reads lower than it should. Below the altitude, the airspeed indication is higher. The greater the altitude change, the greater the error. If the static system becomes blocked while you're changing altitudes, the altimeter freezes in place and the VSI returns to zero. If this occurs, you need to find an alternate source of static pressure. Many aircraft have an alternate static source. On a non-pressurized airplane, it is usually vented to the cabin area. If an alternate source is not available, you could, as a last resort, break the glass on the VSI. With the glass broken, you should consider any VSI readings unreliable. In both cases, the pressure inside the cabin is slightly lower than that surrounding the airplane. Therefore, the altimeter will read higher and the airspeed faster than normal. Because the flight instruments are so critical during IFR conditions, you should take extra care to ensure they are working properly. This includes making sure the static, altimeter, and automatic pressure altitude reporting systems have been inspected within the preceding 24 calendar months. During the pre-flight, visually inspect the static port and pitot tube for obstructions. Once inside the airplane, check that the wings are level in the turn coordinator, that there is fluid in the inclinometer, and that the ball rests in the lowest point. Then when you turn the master switch on, listen to the sound of the electrically driven gyros and make sure there are no abnormal noises. Once the instruments stabilize, continue your inspection by verifying proper alignment of the attitude indicator and turn coordinator. Check that the VSI is indicating 0. If it doesn't, simply apply the error to your in-flight indications. Set the altimeter to the current reported setting and make sure it reads within 75 feet of the airport elevation. Then verify that the airspeed indicator is reading 0. As you begin to taxi, check the heading indicator to verify directional changes during the turn. The turn coordinator should also indicate a turn in the same direction, with the ball shifted away from the turn. Prior to takeoff, make sure you've aligned the heading indicator with the magnetic compass. Then, as you're accelerating for takeoff, quickly glance at the instruments to verify that the gyros are not drifting and that the airspeed indicator is increasing at an appropriate rate. The world of instrument flight is a truly fascinating one. As you gain experience in flying by instruments and become accustomed to the information portrayed on the panel, you'll open up new horizons for your flight.
Attitude instrument flying is the technique of controlling your airplane by using the flight instruments rather than outside visual references. It involves establishing a precise attitude for a given power setting and then maintaining that attitude by reference to the flight instruments. When a change in the airplane's attitude is required, initially make the change by referring to the attitude indicator. Then scan the other instruments as needed for verification. For example, besides the attitude indicator, any change in bank is apparent on the heading indicator and turn coordinator. Pitch changes can be seen on the attitude indicator, altimeter, VSI, and airspeed indicator. Let's take a look at some of the basic maneuvers using instrument references, beginning with straight and level flight. For this maneuver, you need to control both heading and altitude. To maintain the desired heading, establish a wings level attitude on the attitude indicator. Then, monitor the bank instruments for any deviation. If you drift off your desired heading, adjust the attitude indicator to a bank angle that will correct the deviation. You should use a bank angle that equals the number of degrees of correction, as long as it doesn't exceed a standard rate turn. For example, if you're 10 degrees off your desired heading, you should use a bank of 10 degrees to get back on course. In straight and level flight, maintain altitude by establishing the appropriate pitch on the attitude indicator. Normally, the miniature airplane is aligned with the artificial horizon. However, if you increase the airspeed while maintaining level flight, the miniature airplane will be below the horizon. At slower airspeeds, it is above. After you've established level flight for a particular airspeed, you should reset the miniature airplane so it is on the horizon. After the correct attitude has been established, confirm level flight by referring to the altimeter, vertical speed indicator, and airspeed indicator. If your altitude starts to change, look at the VSI to determine the rate of the change. A small rate change will only require a minor correction. You should also check the airspeed indicator to see how the pitch change has affected the airspeed. If the airspeed is extremely fast or slow, you'll have to make a larger correction. When you have determined that a correction is necessary, stop the movement by adjusting the pitch attitude slightly. Then make the necessary adjustments to return to your desired altitude. Normally, if the altitude deviation is less than 100 feet, use a correction of a half bar width. If the deviation is greater than 100 feet, initially use a full bar width. Once the new pitch attitude is established, check the altimeter, vertical speed indicator, and the airspeed indicator to see that you have made the proper correction. Now let's take a look at turns. Most turns are performed at the standard rate of 3 degrees per second. As with straight and level flight, establish the bank using the attitude indicator. You can estimate the approximate bank by dividing your true airspeed by 10 and then adding 5. For example, if your true airspeed is 120 knots, you will be in a standard rate turn if your bank is approximately 17 degrees. You can verify that your turn is coordinated and that you're using the proper bank by referring to the turn coordinator. No matter what the airspeed, if the wing on the instrument is aligned with the mark and the ball is centered, you're in a standard rate turn. When established in the turn, the altimeter and VSI confirm your pitch attitude. If you observe a deviation, adjust the pitch on the attitude indicator and check the altimeter and VSI to see that you have made the proper correction. The airspeed indicator will directly indicate the need for a power change. During your instrument training, you will learn to make turns faster than standard rate. To do this, steepen the bank. As bank increases, the loss of vertical lift causes the aircraft to descend. To compensate, increase the pitch attitude and trim the aircraft. Scan the altimeter and VSI to confirm that your pitch adjustment is correct and that you're maintaining level flight. Since an airplane tends to slow down during a steep turn, you need to increase power to maintain airspeed. Remember to lead the rollout by 1/2 the bank angle. For example, if you're turning to 180 with a bank of 40 degrees, start your rollout at 200 degrees. As you begin the rollout, you need to reduce the pitch attitude and power to maintain level flight. Then retrim the aircraft. When changing altitudes in instrument flight, you should perform either a constant airspeed or constant rate climb or descent. To maintain a constant airspeed, initially adjust the pitch attitude of the airplane by referring to the attitude indicator. During this maneuver, you normally hold a constant power setting. However, if you desire to change the rate of descent or climb, you can vary the power. While performing the maneuver, monitor the airspeed indicator and make small adjustments in pitch attitude to maintain airspeed. Check your heading indicator and turn coordinator to verify straight, coordinated flight. Constant rate maneuvers are performed in a slightly different manner. In this case, the object of the maneuver is to establish a climb or descent at a constant rate. After establishing the approximate pitch and power settings using the attitude indicator and the throttle, verify the correct rate by referring to the vertical speed indicator. If a change occurs, you need to make an adjustment in the pitch attitude. With a constant rate maneuver, adjust the power to achieve the desired airspeed. Approaching your target altitude, use the 10% rule of thumb for leading your level off. In other words, if your descent rate is 500 feet... Then, gently raise the nose to a level flight attitude. Flight instruments, like all mechanical things, are subject to malfunctions. Therefore, you need to know alternate sources for pitch, bank, and heading information if the main sources are inoperative. For example, suppose you notice that your aircraft's attitude indicator is showing a 5-degree bank to the right. However, the heading indicator is not moving. The turn coordinator indicates a left turn, which is confirmed by the magnetic compass. A check of the suction gauge indicates that there isn't sufficient vacuum to drive the gyros. If this happens, the indications on both the attitude and heading indicators are no longer reliable. To complete the flight, you'll have to use the other instruments. When flying partial panel, you must identify the inoperative instruments and omit them from your scan. If they become too distracting, you might find it helpful to cover the instrument faces. With the attitude indicator and the heading indicator no longer functional, your reference for bank information is now the turn coordinator. For pitch information, you must rely on your VSI, altimeter, and airspeed indicator. For heading information, use your magnetic compass. The compass, however, is susceptible to the forces of magnetic dip and acceleration errors, and does not give reliable information during a turn. This necessitates the use of a timed turn to make a heading change. Remember, with the wing aligned on the turn coordinator, your rate of turn will be 3 degrees per second. You can use this figure to calculate how many seconds it will take to turn to a new heading. For example, let's say that you are on a heading of 270 degrees and want to turn to 180. That's a heading change of 90 degrees. At a turn rate of 3 degrees per second, it will take you 30 seconds to reach the new heading. After timing for 30 seconds, begin your rollout. When stabilized in level flight, read the magnetic compass. You may have to make small adjustments to get to the exact heading you desire. In this program, we have looked at some of the maneuvers you'll perform by reference to the flight instruments. Learning how to execute these maneuvers proficiently will greatly assist you when it comes time to start making instrument approaches.
During your VFR training, you learned several methods for keeping track of your position and navigating from one place to another. You learned how to use pilotage and dead reckoning. And you learned basic radio navigation skills using VOR and ADF. As you transfer to instrument flight, your knowledge and understanding of radio navigation must increase, since your outside visual references are replaced by instruments. The ability to visualize your position is one of the most important IFR skills you can develop. It makes IFR navigation much easier. With that in mind, let's review some of the basics of VOR navigation as they relate to IFR flight. We'll begin with this clearance from departure control.
Warrior 312, 5 miles northeast of Jackson VOR, intercept Victor 77 and resume your own navigation.
As you can see, it's always important to know where you are. To intercept the radial, the first thing you need to do is visualize your position in relation to where you want to go. In this case, you are to the east of Victor 77, which is the 020-degree radial from the VOR. With the VOR indicator set to the 020-degree radial, the CDI shows a full-scale deflection to the left. This means you are more than 10 degrees from the radial. To find out where you are, rotate the OBS until the needle centers with a from indication. In this situation, you're located on the 060-degree radial from the station. Now that you know what radial you're on, you need to choose a heading that will enable you to intercept the 020-degree radial. The angle of interception depends on several factors, such as your ground speed and proximity to the radial and navigational aid. A wide range of angles may be suitable. One possibility is to fly a 90-degree intercept to the 020-degree radial. In this case, you need to anticipate your turn onto the airway, since a 90-degree standard rate turn takes 30 seconds. Another choice is to intercept the radial at a smaller angle. For example, a 30-degree angle is commonly used for en route operations. For this intercept angle, you must maintain a heading of 350. As you approach the radial, the CDI helps you anticipate your turn onto the course. At standard rate, the 30-degree turn will take only 10 seconds, so the amount of lead is relatively small. Although the basics of VOR tracking and bracketing are the same for both visual and instrument flight, these skills need to be fine-tuned for IFR navigation. It is important to realize that, as you fly away from a VOR, a deviation from your desired course represents a greater lateral distance. Each dot represents a lateral distance of 200 feet for every nautical mile you travel away from the VOR. For example, at 5 miles from the VOR, a 1-dot deviation means you're about 1,000 feet away from the course. But at 30 miles, this same deflection places you about a mile off course. Another skill you need for IFR navigation is identifying an intersection that is based on VOR. Here, you identify Walto by the intersection of the airway and the 270-degree radial from Duncan VOR. One indicator is used to navigate along the airway. The other one is tuned to the Duncan VOR, with the OBS set at 270 and a from indication. When the needle centers, you are at the intersection. Another method for identifying an intersection, as well as keeping track of your position, is through the use of distance measuring equipment, or DME. The equipment on board your airplane transmits a radio signal to the selected ground facility. This triggers a response back to the aircraft, where the time lapse is translated into your distance and time from the station, as well as your ground speed. Remember that DME measures the slant range distance between your airplane and the ground station, rather than the horizontal distance. Although the slant range error is negligible at long distances and low altitudes, it may become significant at high altitudes when you're close to the station. For instance, if you pass over the station at 12,000 feet AGL, the DME will show approximately 2 miles instead of 0. Now, let's take a look at an instrument that combines the features of the VOR and the heading indicator. The horizontal situation indicator is gaining popularity because of the abundance of navigation information it provides in a pictorial display. The compass card provides you with headings, just like a normal heading indicator. The course selection knob functions like an OBS and moves the course arrow to your chosen radial. The lateral deviation indicator is similar to the CDI and senses your position with respect to the selected radial. The ambiguity indicator functions like the to from indicator and shows whether the selected radial will take you to or from the station. The airplane symbol in the center of the HSI represents your horizontal situation in relation to the nav aid. A glide slope indicator shows your position relative to the glide slope. You'll learn its importance later on when you practice instrument approaches. To see how easy the HSI is to interpret, assume you are southwest of a VOR on a heading of 360 and want to intercept the 270-degree radial and fly inbound to the station. The first thing you do after tuning and identifying the station is to set the inbound course of 090 degrees. Notice the ambiguity needle shows that this course is to the VOR. With an HSI, it is easy to visualize your position. The relationship between the miniature airplane and your intended radial is shown by the lateral deviation needle. You know that you're flying toward the radial at a 90-degree angle. Choosing an intercept angle is simple with an HSI since it provides a visual presentation of your aircraft heading and your selected course. Let's assume you want a 45-degree intercept. After turning the airplane to 045 degrees, notice how the instrument shows your angle as well as your new heading. As you approach the radial, the needle will begin to move towards center to signify that you're nearing the course. You can gradually shallow the angle depending on your rate of closure to smoothly intercept the new course. You might have to adjust your heading slightly to compensate for the wind. Let's now look at the benefits of an automatic direction finder. ADF has a wide variety of uses in the IFR environment. You can use it to receive weather information and to provide position orientation during en route flight and instrument approaches. Since the navigation signals are not limited to line of sight, you can receive them at lower altitudes and greater distances. Let's take a moment to review how bearing information is given. On a fixed card ADF, you determine your magnetic bearing to a station by adding your magnetic heading to the relative bearing. In this case, the magnetic heading is 030 and the relative bearing is 090. This produces a magnetic bearing to the station of 120 degrees. Your text covers the fixed card ADF in detail. With a movable card, you can dial in your magnetic heading and the needle will point directly to the magnetic bearing. To demonstrate how to visualize your position and navigate with ADF, assume you're on an easterly heading and you want to intercept the 360-degree bearing to the NDB and track inbound. After identifying the station, you find that your present position is on the 020-degree bearing to the station, as shown by the head of the bearing pointer. Rather than use a 90-degree angle, you decide to turn left and intercept the bearing at 30 degrees. Your heading in this case is 030 degrees. By setting your magnetic heading under the top index, you can use the head of the bearing pointer to show your position in relation to the bearing. When it indicates 360, you have reached the bearing. In actual practice, you should begin your turn just before you intercept the bearing. This reduces the possibility of overshooting the desired course. Since the ADF does not automatically provide a wind correction angle as a VOR does, let's review the bracketing procedures. In this example, you've drifted right of the 360-degree bearing to the station. The ADF is sensing a crosswind by pointing to 350. To regain the course, you apply a 10-degree correction into the wind and reset the ADF to match your heading. If your heading and relative bearing remain constant, you've corrected for the drift, but you will not intercept the 360-degree bearing. So, an additional correction is needed. In this case, you are using a 20-degree correction angle to regain the course. If you continue to keep the ADF heading aligned with your magnetic compass, you can verify that you have returned to the course when the head of the bearing pointer equals 360 degrees. To remain on course, use just enough crab to maintain this magnetic bearing. The last navigation instrument we'll look at is a radiomagnetic indicator. The RMI lets you continuously monitor your heading as well as your position from two nav aids simultaneously. While one needle indicates your magnetic bearing in relation to an NDB station, the other shows the magnetic bearing to a VOR station. To see how this instrument works, assume you're flying north along an airway on the 180-degree radial of a VOR. An intersection ahead of you on the airway is identified by the 090-degree bearing to an NDB. With an RMI, you can navigate along the airway with one needle while continuously monitoring the ADF pointer. When it points to 090, you are at the intersection. As you continue northward, the bearing pointers provide a perpetual display of your position relative to the two stations. Precision IFR navigation depends on your ability to visualize your position, interpret the instruments, and quickly select headings that will intercept or maintain your desired course. The accuracy of the information you use is a vital part of this process. For this reason, the FARs have established procedures for checking the VOR equipment and the maximum permissible bearing errors for IFR flight. The VOR equipment in the airplane must have been operationally checked within the preceding 30 days. It is your responsibility to ensure all your equipment is within acceptable limits prior to an IFR flight. IFR navigation, attitude instrument flying, and instrument interpretation are the foundation upon which all instrument flying is based. Mastering these skills will enable you to efficiently operate in the IFR environment.
During your private pilot training, you are introduced to the airport environment, the structure of the airspace, and ways to obtain and interpret flight information. This program is designed to review these areas and to provide you with additional information pertinent to commercial and instrument operations. Let's begin with a look at the airport environment. There are several types of signs which provide you with information while taxiing. These signs are mandatory instruction, location, direction, destination, information, and runway distance remaining. First, mandatory instruction signs are used to denote an entrance to a runway or critical area, and to areas where aircraft are prohibited from entering. These signs have white lettering on a red background and usually indicate the holding position for these areas. There are three different types of location signs. The ones used to identify either a runway or taxiway have yellow lettering and a yellow border on a black background. Runway boundary and ILS critical area boundary signs have black markings on a yellow background. Geographic position markers are pink with black lettering and identify a specific location on a taxiway. Direction signs have black lettering on a yellow background and contain arrows that indicate the directions of taxiways leading from an intersection. Destination signs indicate the general direction to remote locations such as runways, terminals, military areas, civil aviation areas, and fixed-based operators. Signs that advise you of nice-to-know items are referred to as information signs. The runway distance remaining sign provides you with valuable information during takeoff or landing. The signs have a white number on a black background and are located along the side of the runway. The number indicates the distance remaining in thousands of feet. Now let's look at an example of the basic VFR markings found on a hard-surfaced runway. They consist of white runway numbers and a center line. When instrument approaches are authorized at an airport, additional markings are added to help you identify the runway environment during reduced visibility. A runway served by a non-precision instrument approach procedure has threshold markings. The runway may also have aim point markings that are located 1,000 feet from the end of the runway. A precision instrument approach runway includes touchdown zone markings that provide distance information in 500-foot increments, as well as side stripes. Thresholds can be marked in two different ways, the first being 8 vertical stripes in 2 sets of 4. A threshold can also be marked with a set of 4 to 16 stripes that indicate the width of the runway. This runway has 16 stripes on the threshold, which indicates a 200-foot wide runway. The threshold is sometimes displaced from the beginning of the paved surface due to noise abatement procedures, obstacles in the approach path, or because the pavement can't support landing loads. In this case, a solid white line across the runway marks the displaced threshold. Special markings leading to the threshold tell you what types of operations are permitted. In this example, the yellow arrows mean you can taxi, take off, and roll out within this area, but you cannot use it for landing. Yellow chevrons mark areas that cannot be used for taxiing, takeoff, or landing. In an emergency, however, this area is available to help decelerate and stop your aircraft when you're approaching from the opposite direction. Another airport marking you should be familiar with is an ILS hold line that protects the critical area of the ILS signal. A runway served by an ILS will have a sign, a hold line, or both that protects the signal from being blocked by aircraft or vehicles. Where 2 sets of hold lines exist, the one closest to the runway is usually marked with the runway number, while the other is marked with a sign indicating it is the ILS hold line. Another hold line marking you need to be familiar with is the hold line on a runway where land and hold short operations are in effect. At busier airports, you may be asked to participate in land and hold short operations, or LAHASO. This is an ATC procedure in which you land on a runway and hold short of an intersecting runway, taxiway, or other specific point on the airport. At airports where LAHASO takes place, there will be a hold line marked on the runway and a hold sign next to the runway. There may also be a row of white pulsing lights installed in the pavement across the runway. As the pilot in command, it is up to you to either accept or reject a LAHASO clearance. You should accept this clearance only if you are confident that, under the existing conditions, you are able to safely land and stop your aircraft in the distance available. The available landing distance for specific hold points is provided in the Airport Facility Directory. Situational awareness is extremely important during LAHASO operations. Should you reject a LAHASO clearance, know that the LAHASO lights and signs will remain on during your approach and landing. Let's turn our attention now to airport lighting. When flying an IFR approach, you must positively identify the runway environment. During periods of low visibility, the first thing you will probably see is the approach lighting system guiding you to the runway. A common approach lighting system is this ALSF-1. It is between 2,400 and 3,000 feet long. A horizontal row of white lights is located 1,000 feet from the runway threshold. One of the first things you will probably see with this system is the sequenced flashing lights. They extend to the distance marker 1,000 feet from the approach end of the runway. The ALSF-2 system includes a row of red lights on each side of the center line and another row of white lights at 500 feet from the runway threshold. This system provides additional runway guidance during the more sophisticated instrument approaches. Most of the other approach lighting systems are variations of the standard system. It's very important to study the approach lights for your destination airport so that you know what to look for as you descend out of the clouds. Several visual approach slope indicator systems are available to help you maintain the proper glide path during the final descent to the runway. The most common system is the 2-bar visual approach slope indicator, or VASI. With this system, white indicates you're above the glide path, while red indicates you're below it. The correct on-glide path indication is red over white. When you're below the glide path, both bars are red. If both bars are white, you're above the glide path. Some airports have a 3-bar VASI system that provides 2 visual glide paths to the same runway. The 2 near bars give you the same glide path indications as the standard 2-bar system. The glide path formed by the 2 far bars is used by high cockpit aircraft and is about 1/4 of a degree steeper than the other glide path. The Precision Approach Path Indicator System, or PAPI, uses a single row of either 2 or 4 lights. Above the glide path, all lights are white. As you descend and move closer to the glide path, the light on the right turns red. As you intercept the glide path, the 2 indicators on the right are red, while the 2 on the left are white. When all the lights are red, you're below the glide path. The lighting on the runway itself also helps you identify the runway environment and maintain your orientation during the final approach. At some airports, you control the airport lights as well as their intensity by keying the microphone a specific number of times within a certain time period. It's important to check the aim for proper procedures to activate the various lighting systems. At most monitored airports or ones with a full-time control tower, you can request the tower or flight service station to temporarily adjust the lights for you. The taxiway lights provide direction while on taxiways, entering and exiting runways, and taxiing to other surface locations on the airport. The amount of lighting varies greatly depending on the size of the airport. Taxiways are outlined in blue lights or blue reflectors. Additional taxiway lighting may be used during periods of low visibility. For example, green taxiway centerline lights may be available at some airports. Yellow, in-pavement clearance bar lights indicate the location of holding points and intersecting taxiways. They are designed to increase awareness of holding positions during periods of low visibility. Runway guard lights are elevated or in-pavement yellow flashing lights that are installed at runway holding positions. They indicate where a taxiway intersects a runway. Stop bar lights consist of a row of red in-pavement lights. They are designed to confirm an ATC clearance to enter or cross an active runway during periods of low visibility. Pilots should never cross an illuminated red stop bar. Each year, hundreds of aircraft are destroyed or damaged by collisions with other aircraft or vehicles on the ground. The majority of these accidents are preventable. All pilots must be more vigilant and become aware of the dangers of runway incursions. Ground operations during low visibility and bad weather can challenge situational awareness. When operating at an airport, always be aware of other aircraft moving around you. Also be aware of situations that increase the likelihood of an incursion. A runway incursion can involve an aircraft, vehicle, person, or object on the ground that creates a collision hazard. A misunderstood clearance can also result in a runway incursion or a potential collision. There are several procedures that you can follow and precautions that you can take to avoid a runway incursion. Complete as many checklist items as possible before taxiing. Concentrate on your primary responsibilities. Do not become absorbed in other tasks or conversation while the aircraft is moving. Read back all clearances involving active runway crossing, hold short, and taxi into position and hold instructions. If you are unsure of your position, stop and ask for assistance. Tower-controlled airports can offer progressive taxi instructions. Report deteriorating or confusing airport markings, signs, and lighting to the airport operator or FAA officials. Also, report confusing or erroneous airport diagrams and instructions. Let's turn our attention now to a review of the National Airspace System. As a pilot, it's important that you understand which flight restrictions and aircraft equipment requirements apply to each type of airspace. Airspace is categorized into regulatory and non-regulatory airspace. These categories are further broken down into controlled airspace, uncontrolled airspace, special use airspace, and other airspace. Controlled airspace consists of those areas designated as Class A, B, C, D, and E airspace. Uncontrolled airspace is designated as Class G. The classification of airspace is relative to the complexity of the operational requirements placed on the pilot and aircraft. With this in mind, let's take a look at Class A airspace. Class A airspace extends from 18,000 feet MSL up to and including 60,000 feet MSL. To fly in Class A airspace, you must hold a current instrument rating and be on an IFR flight plan. In addition to the standard IFR equipment requirements, your aircraft must have an encoding altimeter, a transponder with mode C, and radio equipment capable of communicating with ATC on the appropriate frequencies. Instrument high altitude and route charts must be used for navigation in Class A airspace. If you're using VOR navigation, your aircraft must be equipped with DME for flights above 24,000 feet. It's important to note that a transponder with Mode C altitude reporting capability is required when operating above 10,000 feet MSL in all controlled and uncontrolled airspace within the contiguous United States and the District of Columbia. This excludes the airspace at and below 2,500 feet AGL. Many of the nation's busiest airports are surrounded by Class B airspace. The center of this controlled airspace area usually extends from the surface up to a specified altitude, while the outer areas step up from the surface to form a shape similar to an upside-down wedding cake. The upper and lower limits of each area within Class B airspace are depicted on sectional charts, and the lateral dimensions are shown by a solid blue line. Before entering Class B airspace, you must first receive clearance. Therefore, your aircraft must be equipped with a two-way radio capable of communicating with ATC. In addition, your aircraft must have a transponder with Mode C to operate within 30 nautical miles of the primary airport. This requirement extends from the surface up to 10,000 feet MSL. However, if your aircraft's transponder is inoperable, you may request a deviation from air traffic control. This request must be made at least 1 hour prior to the time you would like to enter their airspace. For IFR operations in Class B airspace, your aircraft must also be equipped with an operable VOR or TACAN receiver. In addition, you must hold at least a private pilot certificate to operate within Class B airspace. Student pilots may operate within this airspace and land at many of the airports within the surface area of this airspace, provided they comply with the restrictions and training requirements in the FARs and have the appropriate endorsement in their logbooks. However, there are some Class B primary airports that are so congested that takeoffs and landings by student pilots are prohibited. These airports are listed in FAR Part 91 and in the AIM. At certain other airports where ATC provides radar services to all aircraft, Class C airspace exists. Typically, this airspace consists of an inner circle that has a 5 nautical mile radius around the primary airport and extends from the surface up to 4,000 feet above the airport elevation. The outer circle has a 10 nautical mile radius and begins at 1,200 feet AGL. It has the same upper limit as the inner circle. There is also an outer area that extends out to 20 nautical miles from the primary airport. The ceiling of this area extends up to the limit of each approach control's delegated airspace, and the floor extends upward from the lower limit of either radar or radio coverage. Therefore, the vertical limits of this airspace varies for each Class C area. The altitudes of the inner and outer circles of Class C airspace are depicted on sectional charts, and the lateral limits are outlined with a solid magenta line. Before you can operate within the inner or outer circle, you must establish and maintain two-way communications with ATC. While not mandatory, you are strongly encouraged to establish and maintain communications with ATC when operating within the 20-mile outer area. To fly within Class C airspace, your aircraft must be equipped with an operable Mode C transponder. This requirement also extends up to 10,000 feet MSL above the lateral limits of this airspace. Class D airspace is designed to provide an orderly flow of traffic around airports with an operating control tower. Before entering this airspace, you must establish and maintain two-way radio communications with the control tower. The lateral dimensions of Class D airspace are normally based on the instrument approach procedures which service the airport. Since this airspace often contains arrival extensions, The lateral limits vary from airport to airport. On sectional charts, these limits are depicted by a blue dashed line. Sectional charts also depict the MSL ceiling of Class D airspace. Normally, this is 2,500 feet above the airport elevation, rounded off to the nearest 100-foot increment. However, if conditions warrant, the ceiling may be higher or lower than the typical 2,500 feet. In some cases, the arrival extensions may not require that you establish contact with the control tower. When this is the case, the extension area is designated as Class E airspace and will be depicted by a dashed magenta line on sectional charts. An airport with a part-time control tower is designated as Class D airspace only when the tower is in operation. The remainder of the time, this area is Class E airspace. Let's take a look at other types of Class E airspace. One area of Class E airspace covers the 48 contiguous states, the District of Columbia, and a portion of Alaska. This area begins at 14,500 feet MSL and ends at the base of Class A airspace, but does not include the airspace within 1,500 feet of the surface. Federal Airways, also known as Victor Airways, are designated as Class E airspace. These airways typically extend from 1,200 feet above ground level up to but not including 18,000 feet MSL and are normally 8 nautical miles wide. Another area of Class E airspace is found around non-towered airports which have approved instrument approach procedures. This includes part-time tower locations when the tower is closed. The purpose of this area is to allow IFR traffic to remain in controlled airspace while transitioning from the en route environment to the airport. When the base of this type of Class E airspace begins at the surface, the lateral limits are depicted on sectional charts with a dashed magenta line. When the base of this airspace begins at 700 feet AGL, the lateral limits are depicted by a magenta shaded boundary. In both cases, the vertical limit extends upward to the base of the overlying airspace. Since this varies from location to location, the upper limit is not depicted on sectional charts. In order for you to conduct VFR operations within the lateral boundaries of Class B, C, D, and E airspace, you must have a ceiling of at least 1,000 feet. In addition, VFR pilots cannot land, take off, or enter the traffic pattern unless the visibility is 3 statute miles or better. These requirements give VFR and IFR pilots the necessary visibility to see and avoid each other during approaches and departures. When weather is below VFR minimums, you may be able to obtain a special VFR clearance from ATC. This allows you to take off and land as long as you have 1 mile visibility and can remain clear of clouds. However, a special VFR clearance cannot be issued at night unless you have a current instrument rating and your airplane is equipped for instrument flight. In addition, special VFR clearances are not issued to fixed-wing aircraft during the day or night at some of the nation's busier airports. You can find a listing of these airports in FAR Part 91, Section 3 of Appendix D. At airports where special VFR is prohibited, no SVFR is printed above the airport name on sectional and terminal area charts. The last letter designation for U.S. airspace is Class G, or uncontrolled airspace. Essentially, all remaining airspace that has not been designated as Class A, B, C, D, or E is uncontrolled. ATC has no responsibility or authority for aircraft operations, nor is there a requirement for pilots to file IFR flight plans in uncontrolled airspace. However, both the pilot and aircraft are required to be fully qualified for instrument flight. Now let's look at airspeed restrictions for both controlled and uncontrolled airspace. Unless otherwise authorized, you cannot operate an aircraft faster than 250 knots when below 10,000 feet MSL, regardless of the type of airspace. When operating below 2,500 feet AGL and within 4 nautical miles of the primary airport of a Class B, C, or D airspace area, the maximum airspeed decreases to 200 knots. This 200-knot limitation also applies to aircraft operating in the airspace below the floors of Class B airspace and in a VFR corridor designated through such airspace. Another major type of airspace is called special use. You may be required to avoid these areas or to abide by certain limitations within them. For example, flight within prohibited areas is not allowed because of national security or other reasons of national welfare. In contrast, flight within a restricted area is not prohibited, although certain limitations may be imposed due to hazards in the area. VFR flights must contact the controlling agency, while an IFR clearance through the area constitutes an authorization to penetrate the airspace. Warning areas are over coastal and international waters and cannot be designated as restricted. However, the activities within these areas may be as hazardous as restricted areas. An alert area contains a high volume of pilot training or an unusual type of aerial activity. Flight within alert areas is not restricted, but you are urged to exercise extreme caution and remain alert for other traffic. Military operations areas, or MOAs, are established to separate certain military training activities from IFR traffic. When flying IFR, you may be cleared through an active MOA if ATC can provide separation. If you are flying VFR, you should exercise extreme caution within an active MOA. Another type of airspace is called other airspace areas. An example of 2 types of airspace in this classification are military training routes and airport advisory areas. Both IFR and VFR military training routes are depicted on sectional and government en route charts. Flight operations along these routes are typically flown below 10,000 feet MSL at speeds in excess of 250 knots. An airport advisory area exists at airports that have a flight service station but don't have an operating control tower. The FSS provides a local airport advisory service to all participating aircraft within a 10 statute mile radius. Visibility and cloud clearance minimums are also important considerations when operating in the national airspace system. When you fly VFR at or above 10,000 feet MSL and are more than 1,200 feet AGL, you're required to have a flight visibility of at least 5 statute miles. You must also have at least 1 statute mile horizontal and 1,000 feet vertical separation from all clouds. When you're below 10,000 feet MSL, but more than 1,200 feet AGL, VFR minimums require you to maintain a minimum flight visibility of 3 statute miles in controlled airspace. This also applies to uncontrolled airspace at night. During the day in uncontrolled airspace, the visibility lowers to 1 statute mile. You must also maintain 2,000 feet horizontal separation and remain 500 feet below and 1,000 feet above any clouds. If you're at or below 1,200 feet AGL in controlled airspace or uncontrolled airspace at night, regardless of MSL altitude, you must maintain a flight visibility of 3 statute miles and maintain 2,000 feet horizontal separation, 500 feet below and 1,000 feet above any clouds. However, in controlled airspace, you may operate an aircraft in an airport traffic pattern at night within 1/2 mile of the runway with a minimum visibility of 1 mile while remaining clear of clouds. You can also operate VFR in Class B airspace with 3 miles visibility and clear of clouds. At or below 1,200 feet AGL in Class G airspace during the day, you must remain clear of all clouds and maintain 1 statute mile visibility. Let's turn our attention now to a review of the flight information publications. These publications help you meet your FAR requirement to familiarize yourself with all the available information concerning each flight. The Airport Facility Directory contains information pertinent to both VFR and IFR flight planning. The directory legend provides a thorough breakdown of the abbreviations and symbols used in the airport listings. Although most of the directory is devoted to airport and facility listings, there are other sections that contain essential flight information. For example, the Special Notices section includes hard-to-find but significant information about a wide variety of subjects. You should review this section frequently for changes that might affect your flight. The remaining sections provide telephone numbers for FAA and National Weather Service outlets, Air Route Traffic Control Center frequencies, preferred IFR routes, VOR receiver checkpoints, parachute jumping areas, aeronautical chart bulletins, upper air observation stations, and en route flight advisory service outlets. The Aeronautical Information Manual, or AIM, is a comprehensive reference source that covers VFR and IFR flight operations. It includes information that helps you efficiently operate in the National Airspace System, such as the various navigation aids available, aeronautical lighting and other airport visual aids, a thorough discussion of regulatory and non-regulatory airspace, and ATC procedures. Since the AIM is revised several times a year, you should study and review it periodically. Let's look now at a system that provides time-critical flight information. The Notices to Airmen publication and the NOTAM Telecommunications Network are designed to pass along changes in the National Airspace System. These changes are either temporary or not available in time to include in other documents, such as the Airport Facility Directory or aeronautical charts. A NOTAM may be classified as either a NOTAM D, NOTAM L, or an FDC NOTAM. A NOTAM D contains information which could affect your decision to make a flight, such as the airport being closed, inoperative nav aids, or interruptions in radar services. This type of NOTAM is not only distributed locally, but is given distant dissemination as well. NOTAM L information is only maintained by the local FSS that is responsible for the airport and is not distributed outside the coverage area. It can include such information as men and equipment near or crossing the runways, taxiway closures, and airport lighting outages. FDC NOTAMs are issued to amend instrument approach procedures and aeronautical charts. It is extremely important to check these prior to an IFR flight and update your flight information where necessary. During your pre-flight weather briefing, you should make sure you receive the latest NOTAMs for your flight. NOTAMs printed in the Notices to Airmen publication are not normally included in the briefing. Therefore, you should always check this publication during your pre-flight planning. Another valuable reference source is the Jeppesen Airport and Information Directory, more commonly referred to as the J-AID. It is a comprehensive collection of current aeronautical and airport information. The J-AID covers the material in the AIM and Airport Facility Directory, as well as many other areas. FAR Part 135 operators are authorized to use it as a substitute for the AIM and Airport Facility Directory. For those pilots who use GPS or LORAN equipment, Jeppesen also publishes a coordinate directory for all public airports, navaids, and waypoints within the U.S. The Internet is also a valuable tool for pilots. You can access information on all aspects of flying. The government maintains websites that allow you to access FAA information such as FARs, advisory circulars, testing information, and practical test standards. A thorough understanding of airports, airspace, and the sources of flight information is essential to operate efficiently in today's national airspace system. Whether you're in VFR or IFR weather, to fly informed is to fly with confidence and safety.
When flying in VFR conditions, you're required to maintain specific visibility and cloud clearance minimums. Instrument flight rules allow for appropriately rated pilots and specially equipped aircraft to fly in weather where normal VFR flight would be impossible or very dangerous. When you're flying in IFR conditions, seeing and avoiding other air traffic may be impossible due to the lack of adequate visibility. During these periods, you must rely on the air traffic control system to keep your aircraft separated from other IFR traffic. For discussion purposes, we have divided the ATC system into two primary sections: terminal facilities, which serve pilots operating in the vicinity of an airport, and en route center facilities, which serve IFR flights outside of the terminal areas. Let's take a look at the larger en route centers first. There are several air route traffic control centers in the United States sharing the responsibility for the coordination and separation of en route IFR traffic operating within controlled airspace. Each area is further divided into sectors, separated both geographically and by altitude. The number of sectors and the altitudes that an individual controller may handle will vary, depending on the air traffic load. Controllers monitor the IFR traffic within these sectors with the aid of a computer-enhanced radar system. To assure safe distances between aircraft, they periodically make adjustments in an aircraft's speed, heading, or altitude. When you file your flight plan, the procedures for achieving IFR traffic separation for your flight are set into motion. The FSS specialist forwards your flight plan to the ARTCC facility from which your flight will originate. There, it is processed and the selected route of flight is approved or amended as necessary. Then, when you depart, your flight information is relayed by computer to the various centers you will be going through. In addition to their first priority of providing separation to all IFR aircraft, En route centers also provide additional safety-related services to IFR and, if conditions permit, VFR aircraft. One of these services is traffic advisories. Whenever possible, the controller will advise you of conflicting VFR traffic. Unfortunately, radar cannot detect all conflicting traffic, especially those operating without a transponder. Therefore, when flying in VFR conditions, even if you're on an IFR flight plan, you are responsible for seeing and avoiding other aircraft. Another service includes the issuance of weather advisories, which alert pilots to potentially dangerous weather phenomena. Center controllers also provide safety alerts, warning IFR pilots who are flying too low for safe terrain clearance. These safety alerts have helped avert many potential accidents. Emergency assistance is another service provided to both IFR and VFR aircraft by the en route center. If this service is needed, ATC can give you priority and clear the airspace of other traffic, or they can give you radar vectors to the nearest airport. They will also assist you if you become disoriented. The second component of the air traffic control system is the terminal control facilities, which serve the airspace surrounding various airports. These facilities are comprised of approach and departure control, the control tower, ground control, and clearance delivery. At busy airports, clearance delivery is a special frequency designed to relieve congestion on the ground control frequency. Generally, you will contact this facility when you have received ATIS information and are ready to depart. Upon receiving your clearance, you contact ground control when you're ready to taxi. At airports without a clearance delivery, you receive your clearance instructions directly from ground control. The control tower operates in much the same way for IFR flights as it does for VFR flights. However, for IFR flights, the tower controller will hand you off to departure control when you're about a half-mile beyond the runway end. Departure and approach control provide IFR separation and handling during the departure and arrival phases of the flight. In metropolitan areas, a single radar facility often handles aircraft operating to or from several nearby airports. They also work closely with the en route center and the tower to transition air traffic smoothly between the terminal and en route airspace structures. As your instrument training progresses, you will become more familiar with all components of the ATC system and how they are used during the course of your flight. Although we have seen many different aspects of the system, you will find the same basic operating procedures apply to them all.
Wire 81312 is cleared to the Cheyenne Airport as filed. Climb and maintain 8,000. Denver departure will be 120.9er. Squawk 5417.
In order to fly in controlled airspace when the weather is below VFR minimums, you must file an IFR flight plan and receive an ATC clearance. An ATC clearance is your authorization to proceed to your destination while maintaining the rules established for instrument flight. In order for ATC to provide the proper aircraft separation, you must not deviate from the clearance unless you are experiencing an emergency or receive an amended clearance. Therefore, if it's apparent that the clearance will, in some way, jeopardize the safety of your flight, you should request an amendment. For example, let's say that you receive these instructions before you take off.
Clear to the Carlsbad Airport is filed. Climb and maintain 15,000.
Your aircraft, however, is not equipped with supplemental oxygen, making the proposed flight at 15,000 feet unsafe and illegal in a non-pressurized aircraft. In this case, you need to request an amendment to your altitude prior to departure. Sometimes the clearance you receive is different from the one you requested. For this reason, pay close attention when copying it and note any changes from your planned route. You should not attempt to copy the information when you're in the process of taxiing or performing other flight duties. If ATC advises you that your clearance is ready to copy, you should ask the controller to stand by.
Warrior 312, clearance. Cincinnati ground, Warrior 312, stand by. Cincinnati ground, Warrior 312, ready to copy. Warrior 81312 is cleared to the Greater Pittsburgh Airport, Lunken 1 departure, Appleton transition, then as filed. Maintain 2,500, expect 10,010 minutes after departure. Contact departure control on 124.5, squawk 5415. Roger, Warrior 81312 is cleared to the Greater Pittsburgh Airport, Lunken 1 departure, Appleton transition, then as filed. Maintain 2,000.
Although a complete readback isn't required, you're expected to read back altitude assignments and any instructions requiring verification. You should also repeat the clearance if you feel the need for confirmation, especially if it differs from the one you were anticipating. To assist you when copying clearances, they are always given in a particular order, beginning with the aircraft's identification, then the clearance limit, departure procedure, route of flight, altitude, holding instructions if appropriate, any special information, and frequency and transponder code. Now let's look at some of these elements in more detail. The first item is always the aircraft's identification.
Warrior 81312.
Following the ID is the clearance limit.
Cleared to the Greater Pittsburgh Airport.
Usually this is your destination airport. However, it could be an intersection, nav aid, or DME fix short of your destination. For example,
Cleared to Atwo intersection. Expect further clearance at 1132.
an expect further clearance time, EFC, should always be given if your clearance limit is short of your destination. You should expect new instructions at least 5 minutes before reaching the clearance limit. At this point, the controller will approve you to fly beyond the fix or instruct you to enter into a holding pattern. A holding pattern is a maneuver designed to keep your airplane within specified airspace limits while waiting for a further clearance. Unless an emergency exists, you should not proceed beyond the clearance limit without ATC approval. Following the clearance limit is any specified departure procedure.
Lunken 1 departure, Appleton transition.
This may be a special procedure called an instrument departure procedure. Or it could also be a specific heading or altitude to fly after takeoff. Departure procedures are published for certain controlled airports. Each has a procedure name followed by a number. This example shows the Lunken 1 departure at Cincinnati. Departure procedures will be covered in more detail in a later program. The route of flight is the next item. When there are no changes in your filed route, ATC may just clear you as filed. Note that this only applies to the route portion of your flight plan. Also notice that even though the departure procedure is part of your flight plan route, it was still given as a separate item in the clearance. When the clearance is not as filed, ATC route instructions may contain any combination of designated airways, VOR radials, courses, or radar vectors. The next item is the assigned altitude.
Maintain 2,500, expect 10,010 minutes after departure.
You will always get an assigned altitude even if you've been cleared as filed. However, instead of a specific altitude, you can request VFR on top. This allows you to remain on an IFR flight plan, but lets you fly at any VFR cruising altitude, from the minimum IFR altitude up to but not including 18,000 feet, as long as you're able to stay in VFR conditions. When necessary, holding instructions are the next item in the clearance.
Unless the pattern is charted, holding instructions contain the following: direction of hold in relation to the holding fix, the name of the fix, and the radial, course, bearing, or airway which you are to hold on. Finally, the holding instructions contain an expect further clearance time.
Hold southwest of Atwu intersection on Victor 115. Expect further clearance 1132.
The final items in the clearance are the assigned radio frequency and transponder code.
Contact departure control on 124.5, squawk code 5415.
Not all of your clearances will be complicated or lengthy. For example, you might be issued this clearance.
ATC clears Cessna 52241 to Snyderville Airport as filed, cruise 6000. Contact departure control on 123.8, squawk 5263.
A cruise clearance authorizes you to climb, descend, or cruise at any altitude between the assigned altitude, 6,000 feet, and the minimum IFR altitude. You are not required to report altitude changes to ATC. However, once you do report leaving a specific altitude, you cannot return to it without ATC authorization. The cruise clearance also allows you to use any approved IFR approach procedure at your destination. On long flights, you can expect to be handed off to different ARTCC controllers.
Cessna 52241, contact Albuquerque Center on 132.8 at Las Vegas.
In some cases, a considerable amount of time may pass from when you first receive the new frequency until you actually make contact with the next controller. Therefore, you should always record each frequency as it is received. After you have received the initial clearance, it may be necessary for ATC to make modifications or amendments. Any conditions or instructions given later take precedence over previous instructions. An example of an additional clearance would be an approach instruction given when you reach your destination.
Cessna 52241, 15 miles north of the Carlsbad Airport, you're cleared for approach.
The term cleared for approach means that you have the option of flying any published instrument approach to the airport. On the other hand, if you are given the following clearance,
Cleared for the ILS runway 3 approach.
you are authorized to fly only that particular approach. To aid you in copying clearances quickly and accurately, clearance shorthand symbols have been devised for frequently used words or phrases.
You'll find a complete listing of the symbols in Chapter 3 of your manual. You can use these symbols or devise your own. However, the test of any good shorthand is whether or not you can read and understand a clearance after it's no longer fresh in your mind. If you can, then you've developed a good system for taking shorthand.
To see how this works, let's take the following example.
ATC clears Warrior 81312 to the Greer Airport. After takeoff, climb on a heading of 010. Cross Boyles intersection at or above 2,000 feet. Victor 54 to Spartanburg, direct Greer. Maintain 5,000. Contact departure control on 119.8 at Holly intersection. Squawk 1100.
That clearance would be very difficult to copy using longhand. Now let's see how that same clearance would appear using shorthand.
ATC clears Warrior 81312 to the Greer Airport. After takeoff, climb on a heading of 010. Cross Boyles intersection at or above 2,000 feet. Victor 54 to Spartanburg, direct Greer. Maintain 5,000. Contact departure control on 119.8 at Holly intersection. Squawk 1100.
An ATC clearance is required anytime you are flying in controlled airspace when the weather is below VFR minimums. Understanding how a clearance is presented, knowing the terminology involved, and learning to take good IFR clearance shorthand will help you operate more easily within the ATC system.
To expedite an orderly and safe flow of IFR departures at busy terminal areas, Instrument Departure Procedures, or DPs, were created. These procedures and charts simplify departure for you and controllers, provide a transition between the airport and en route structure, as well as reduce frequency congestion. For example, prior to DPs, a clearance might have sounded like this.
Cessna 385 X-Ray Yankee cleared to the Salt Lake City Airport as filed. Maintain 17,000. Maintain runway heading until reaching 9,000. Turn left heading 250. Intercept the 268-degree radial of Denver Vortac. Cross super intersection at or above 13,300. Denver departure will be 123.85, squawk 1425.
Imagine the time it would take and the problems it could cause to repeat this type of clearance for every aircraft taking off at places like JFK in New York, O'Hare in Chicago, Los Angeles International, or Denver International Airport. DPs help alleviate this communications congestion by consolidating several individual procedures into one standard procedure. This is what the clearance might sound like if you received it with an instrument departure procedure.
Cessna 385 X-Ray Yankee cleared to the Salt Lake City Airport, Denver 3 departure then as filed. Maintain 17,000, squawk 1425.
Notice that Denver 3 departure replaced several procedures in the previous clearance. This not only saves communication time, but makes it less likely you'll receive a clearance you don't understand. Clearances for instrument departure procedures are issued at the option of ATC. If you don't have the graphic or textual information for the DP with you, you should not accept the clearance. If you don't want to use a DP, you should indicate no DP in the remarks section of your flight plan. All instrument departure procedures provide you with obstacle clearance. DPs can be either textual or graphic. Textual procedures, referred to as IFR departure procedures outside the U.S., exist only for obstacle clearance and can normally be found at the bottom of Jeppesen airport charts. If ATC does not assign a graphic DP or other instructions, you can use the textual DP for obstacle clearance to depart the airport and, in some cases, to transition to the en route structure. The FAA is converting some complex textual departure procedures into graphic procedures to improve situational awareness. Graphic procedures are published as separate charts and can be filed as part of a flight plan. When a graphic departure procedure is created only for obstacle clearance, it is labeled obstacle and may contain the statement, if not assigned a departure procedure by ATC, this procedure may be flown to provide obstacle clearance. ATC departure procedures, referred to as SIDS outside the U.S., do not have the obstacle label. These procedures also provide obstacle clearance, but are established primarily to simplify pilot-controller communications, expedite the flow of traffic, and to help with noise abatement. Due to the dynamic nature of instrument procedures and charts, you may see more changes to DPs in the future. Now let's take a look at a few typical DPs and see how they are constructed and what each part means to you. For ease of access, Jeppesen files DPs with all the other charts serving the terminal area. The chart date, index number, and in some cases the effective date are listed at the top of the chart. Notice that the 10-3 type chart index numbers indicate DPs. A departure procedure is often named after the last fix for the common portion of the procedure, prior to the departure transitions. In this case, Merrick intersection. This particular procedure is called the Merrick 3 departure. When a significant change in the procedure occurs, the name changes to the next higher number. At the next major revision, this DP will be renamed the Merrick 4 departure. Obstacle graphic or ATC DPs are one of two types, either pilot nav or vector. The most common graphical depiction is the pilot nav DP, where you, as the pilot, have the primary responsibility for navigation. And the other is the vector DP, where a controller vectors or directs you to fly a certain heading in order to intercept a fix or radial along the flight path. Since this is a pilot nav DP, it is noted near the name of the procedure. The name of this chart is the Merrick 3 departure, which serves the Meadows Airport at Bakersfield, California. As was mentioned earlier, a DP provides an obstacle-free flight path. This is based, however, on your aircraft climbing at 200 feet per nautical mile after it crosses the end of the runway, at least 35 feet above the ground. A slope of 152 feet per nautical mile is assessed for any obstacles. If none penetrate this slope, the 200 foot per mile climb gradient gives you a minimum of 48 feet of obstacle clearance for each mile of flight. When an obstacle, such as rising terrain, penetrates this gradient, obstacle avoidance procedures must be specified in either a textual or graphic format. One of these procedures is to incorporate a climb gradient greater than 200 feet per nautical mile. If you filed and expect to be assigned the Gorman transition, the minimum climb gradient is 220 feet per nautical mile to 9,500 feet. Note that the climb gradient is in feet per nautical mile. Since your VSI only measures feet per minute, you must convert the climb gradient into something which is easily measured. Jeppesen provides this information in a convenient table for various ground speeds. For example, if your ground speed is 100 knots, you must maintain a climb rate of at least 367 feet per minute. Pilot nav DPs usually consist of departure routes identified by bold lines and transition routes identified by dashed lines. The departure routes all terminate at a fix, in this case, the Merrick intersection, where the transition routes begin. A transition route name usually corresponds to the name of the fix where the transition route ends. For example, the Gorman transition terminates at the Gorman Vortac. When DP charts cover large geographical areas, they may not be drawn to scale. This means distances cannot be accurately measured with a plotter. On some DPs, the distance from the airport or runway to the DP fix will be given, such as direct distance from Meadows Airport to Merrick intersection, 16 nautical miles. This value is included to help you determine the approximate mileage for flight planning purposes. However, actual track mileages are depicted along the transition routes. When filing an IFR flight plan that incorporates a DP, you should use the computer departure code, including the departure name and, if appropriate, transition name. For example, if you're using the Merrick 3 departure to Merrick intersection and then proceeding en route from there, the code MARIC3.MARIC should be used on the flight plan. If the flight is composed of a departure and transition route, such as the Gorman transition, the code MARIC3.GMN should be used. By using the computer codes, you not only help the flight service station specialist, but you also help yourself. Since the computer codes won't have to be looked up, the specialist spends less time entering the flight plan into the computer. This should enable you to receive your clearance in a minimal amount of time. You must carefully review any departure procedure, required performance and equipment criteria. Some high-performance procedures are depicted here. The other type of instrument departure procedure is the vector DP. An example of this type of DP is the Denver 3 departure. Notice that this DP does not contain any departure or transition routes. Instead, the controller provides vectors to any one of several fixes. When filing a vector DP, a depicted termination fix where the filed or assigned en route structure begins should be in your flight plan. This type of departure can be used by various types of aircraft. Vector DPs require two-way radio communication, and the lost communications procedures detailed in the FARs apply unless lost comm procedures are published for the departure. In the case of the Denver 3 departure, if communication is lost, you must comply with the procedure titled Lost Communications Procedure Only. Let's take a brief look at the relationship between a graphic DP and a textual DP. Notice the high initial minimum en route altitudes in this graphic departure procedure. Now let's look at the associated textual departure procedure. Note the altitude requirement for aircraft departing westbound from Denver between the 234 and 312 degree radials to ensure obstacle clearance. If you're flying this textual DP for your initial departure, you must climb in the Denver VOR holding pattern until at or above 11,500 feet before proceeding westbound. Pilot nav and vector DPs have a number of advantages for IFR departures, including reduced workload for both pilots and controllers. Remember, all DPs make your climb out safer by providing an obstruction-clear flight path when you depart the airport. In the case of pilot nav DPs, vector DPs, and some textual DPs, this extends to your transition to the en route structure. To expedite an orderly and safe flow of IFR departures at busy terminal areas, Instrument Departure Procedures, or DPs, were created. These procedures and charts simplify departure for you and controllers, provide a transition between the airport and en route structure, as well as reduce frequency congestion. For example, prior to DPs, a clearance might have sounded like this.
Cessna 385 X-Ray Yankee cleared to the Salt Lake City Airport as filed. Maintain 17,000. Maintain runway heading until reaching 9,000. Turn left heading 250. Intercept the 268 degree radial of Denver Vortac. Cross super intersection at or above 13,300. Denver departure will be 123.85, squawk 1425.
Imagine the time it would take and the problems it could cause to repeat this type of clearance for every aircraft taking off at places like JFK in New York, O'Hare in Chicago, Los Angeles International, or Denver International Airport. DPs help alleviate this communications congestion by consolidating several individual procedures into one standard procedure. This is what the clearance might sound like if you received it with an instrument departure procedure.
Cessna 385 X-Ray Yankee cleared to the Salt Lake City Airport, Denver 3 departure then as filed. Maintain 17,000, squawk 1425.
Notice that Denver 3 departure replaced several procedures in the previous clearance. This not only saves communication time, but it makes it less likely you'll receive a clearance you don't understand. Clearances for instrument departure procedures are issued at the option of ATC. If you don't have the graphic or textual information for the DP with you, you should not accept the clearance. If you don't want to use a DP, you should indicate no DP in the remarks section of your flight plan. All instrument departure procedures provide you with obstacle clearance. DPs can be either textual or graphic. Textual departure procedures exist only for obstacle clearance and normally can be found at the front of the terminal procedures booklet. If ATC does not assign a graphic DP or other instructions, you can use the textual DP for obstacle clearance to depart the airport, and in some cases, to transition to the en route structure. The FAA is converting some complex textual departure procedures into graphic procedures to improve situational awareness. Graphic procedures are published as separate charts and can be filed as part of a flight plan. When a graphic departure procedure is created only for obstacle clearance, it is labeled Obstacle and may contain the statement, "If not assigned a departure procedure by ATC, this procedure may be flown to provide obstacle clearance." ATC departure procedures, referred to as SIDS outside the U.S., do not have the obstacle label. These procedures also provide obstacle clearance, but are established primarily to simplify pilot-controller communications, expedite the flow of traffic, and to help with noise abatement. Due to the dynamic nature of instrument procedures and charts, you may see more changes to DPs in the future. Now let's take a look at a few typical DPs and see how they are constructed and what each part means to you. For ease of access, DPs are located immediately following the approach and airport charts for the respective airport. If multiple DPs exist, they are filed alphabetically by the DP name. The index at the beginning of each booklet shows which airports have DPs available. A departure procedure is often named after the last fix for the common portion of the procedure, prior to the departure transitions. In this case, Merrick intersection. This particular procedure is called the Merrick 3 departure. When a significant change in the procedure occurs, the name changes to the next higher number. At the next major revision, this DP will be renamed the Merrick 4 departure. Obstacle graphic or ATC DPs are one of two types, either pilot nav or vector. The most common graphical depiction is the pilot nav DP, where you as the pilot have the primary responsibility for navigation. And the other is the vector DP, where a controller vectors or directs you to fly a certain heading in order to intercept a fix or radial along the flight path. Since this is a pilot nav DP, it is noted near the name of the procedure. The name of this chart is the Merrick 3 departure, which serves Meadows Field at Bakersfield, California. As was mentioned earlier, a DP provides an obstacle-free flight path. This is based, however, on your aircraft climbing at 200 feet per nautical mile after it crosses the end of the runway at least 35 feet above the ground. A slope of 152 feet per nautical mile is assessed for any obstacles. If none penetrate this slope, the 200 foot per mile climb gradient gives you a minimum of 48 feet of obstacle clearance for each mile of flight. When an obstacle, such as rising terrain, penetrates this gradient, obstacle avoidance procedures must be specified in either a textual or graphic format. One of these procedures is to incorporate a climb gradient greater than 200 feet per nautical mile. If you filed and expect to be assigned the Gorman transition, the minimum climb gradient is 220 feet per nautical mile to 9,500 feet. Note that the climb gradient is in feet per nautical mile. Since your VSI only measures feet per minute, you must convert the climb gradient into something which is easily measured. This can be accomplished by referring to the rate of climb table at the beginning of the booklet. For example, if you need to climb at 300 feet per nautical mile and your ground speed is 80 knots, you must maintain a climb rate of at least 400 feet per minute. Pilot nav DPs usually consist of departure routes identified by bold lines and transition routes identified by thinner lines. The departure routes all terminate at a fix, in this case, the Merrick intersection, where the transition routes begin. A transition route name usually corresponds to the name of the fix where the transition route ends. For example, the Gorman transition terminates at the Gorman Vortac. When DP charts cover large geographical areas, they may not be drawn to scale. This means distances cannot be accurately measured with a plotter. On some DPs, the distance from the airport or runway to the DP fix will be given, such as approximate distance from takeoff area to Merrick intersection, 16 nautical miles. This value is included to help you determine the approximate mileage for flight planning purposes. However, actual track mileages are depicted along the transition routes. When filing an IFR flight plan that incorporates a DP, you should use the computer departure code, including the departure name and, if appropriate, transition name. For example, if you're using the Merrick 3 departure to Merrick intersection and then proceeding en route from there, the code MARIC3.MARIC should be used on the flight plan. If the flight is composed of a departure and transition route, such as the Gorman transition, the code MARIC3.GMN should be used. By using the computer codes, you not only help the flight service station specialist, but you also help yourself. Since the computer codes won't have to be looked up, the specialist spends less time entering the flight plan into the computer. This should enable you to receive your clearance in a minimal amount of time. You must carefully review any departure procedure, required performance and equipment criteria. Some high-performance procedures are depicted here. The other type of instrument departure procedure is the vector DP. An example of this type of DP is the San Francisco 8 departure. Notice that this DP does not contain any departure or transition routes. Instead, the controller provides vectors to any one of several fixes. When filing a vector DP, a depicted termination fix where the filed or assigned en route structure begins should be in your flight plan. This type of departure can be used by various types of aircraft. Vector DPs require two-way radio communication, and the lost communications procedures detailed in the FARs apply unless lost comm procedures are published for the departure. In the case of the San Francisco 8 departure, if communication is lost, you must comply with the procedure titled Lost Communications. Let's take a brief look at the relationship between a graphic DP and a textual DP. Notice the high initial minimum en route altitudes and flight level in this graphic departure procedure. Now let's look at the associated textual departure procedure. Note the altitude requirement for aircraft departing westbound from Denver between the 234 and 312 degree radials to ensure obstacle clearance. If you're flying this textual DP for your initial departure, you must climb in the Denver VOR holding pattern until at or above 11,500 feet before proceeding westbound. Pilot nav and vector DPs have a number of advantages for IFR departures, including reduced workload for both pilots and controllers. Remember, all DPs make your climb out safer by providing an obstruction-clear flight path when you depart the airport. In the case of pilot nav DPs, vector DPs, and some textual DPs, this extends to your transition to the en route structure. The departure procedure you use during an IFR flight varies from airport to airport. Sometimes it may be as simple as a climbing turn to your intended course. At other times, it may involve a complicated set of courses, altitudes, and vectors. Therefore, before making an IFR departure, you should acquaint yourself with the procedures which are available at your airport. By regulation, before any IFR flight, you must check the en route weather and the weather at your destination and departure airports. For commercial flights operating under Part 121, 125, or 135 of the Federal Aviation Regulations, certain visibility requirements must be met before a takeoff is allowed. While these minimums are not required for flights conducted under Part 91, they are good guidelines for you to follow. For aircraft with 1 or 2 engines, the standard visibility minimums for takeoff are 1 statute mile. Because some airports have obstructions such as rising terrain, a minimum ceiling, as well as an increase in the visibility, may be required. If the minimums are higher than standard, they will be noted on NOS charts by a triangle symbol enclosing a T. This symbol is found in the information box and can also indicate that departure procedures are published. To determine the exact minimums, you need to refer to the IFR Takeoff Minimums and Obstacle Departure Procedures section in the front of the Terminal Procedures booklet. For example, at Daytona Beach, the takeoff minimums for runways 7 right, 16, 25 left, and 34 are a 300-foot ceiling and 1 mile visibility. Jeppesen prints this information on the airport chart. Since the takeoff minimums are normally based on visibility, let's look at the various types which are reported at an airport. Prevailing or tower visibility is the greatest distance a weather observer or tower controller can see throughout at least 1/2 the horizon circle. It is measured in statute miles or fractions of miles. Runway visibility value, or RVV, is the distance down the runway that you can see unlighted objects or lights of moderate intensity. This value is generally derived from an electronic measuring device and is listed in miles or fractions of miles. When available, RVV is used instead of prevailing or tower visibility. The most accurate reading of visibility along a specific runway is the RVR, or Runway Visual Range. This value is based on measurements from transmissometers located near the runway and relates the horizontal visibility in hundreds of feet. An RVR value of 12 means that the visibility is 1,200 feet. Since the visibility may vary from one runway to another and at different portions on the same runway, especially at larger airports, the RVR value should be used only for the specified runway. Once you have determined that the weather will allow you to make a takeoff, you need to consider what type of departure procedure you're likely to use. When departing an airport, you must climb at a rate of at least 200 feet per nautical mile. This allows at least 48 feet of obstacle clearance for every nautical mile you travel. If obstacle clearance requirements are not met, a textual or graphic departure procedure will be published. These departures are designed according to the criteria established in the United States Standard for Terminal Instrument Procedures, abbreviated TIRPS. NOS publishes the obstacle textual departure procedures with the takeoff minimums at the beginning of the Terminal Procedures booklet. Jeppesen prints them on the airport charts. Departures from airports near large metropolitan areas are usually conducted under radar coverage. A series of heading assignments, called vectors, are provided to transition you from takeoff to the en route portion of your flight. In these cases, the tower generally gives you an initial heading to fly. A short time after liftoff, the tower will instruct you to contact departure control. After changing to the departure frequency, your initial call should include your ID, current altitude, and the altitude to which you're climbing.
Departure Cessna 52241, 2,500, climbing to 5,000.
By stating your current altitude, the controller can verify the accuracy of your Mode C transponder.
Cessna 241, roger, radar contact.
Radar contact is used by the controller to let you know that your aircraft has been identified. However, it is your responsibility to maintain adequate obstacle clearance until the controller issues you a vector or other instructions. Departure control will then give you specific headings to fly in order to intercept your clearance route. Once the final vector has been given, the controller will tell you to resume own navigation. This phrase means that the controller now expects you to navigate using your own equipment. It does not mean that your flight is no longer in radar contact. When departing an airport without an operating control tower, some additional procedures may apply. For example, you might use a ground communications outlet. You may be issued a clearance void time. ATC uses this procedure to reserve airspace around the airport. If you do not depart before this time, your clearance will be canceled. When climbing to your assigned altitude, ATC expects you to climb at the optimum rate for your aircraft until you're within 1,000 feet of your target altitude. Then, slow your rate to 500 to 1,500 feet per minute until you begin to level off. If you cannot maintain at least 500 feet per minute throughout the climb, you must notify ATC of your actual rate. In addition to providing obstacle clearance, at busier airports, instrument departure procedures, or DPs, expedite the flow of air traffic by reducing the length and complexity of issued clearances and by cutting down on pilot-controller communications. As with any IFR departure, DPs also assure adequate obstacle clearance. Some instrument departure procedures contain specific performance requirements in order to maintain adequate obstacle clearance. You should always review the graphic instrument DP chart you're planning to use to verify that your aircraft can comply with the required performance criteria. If you cannot meet these requirements, you should request no DP on your flight plan. A graphic instrument departure procedure requires you to fly a specific route and altitude combination after takeoff. For example, let's take a look at the Gorman transition of the Merrick 3 departure at Bakersfield, California. To fly this pilot nav departure procedure, first look at the takeoff information for the runway in use. In this case, as soon as you take off from runway 12 left, you're required to make a right turn to a heading of 240. From there, the procedure calls for you to intercept the 196-degree radial of the Shafter Vortac and proceed to Merrick intersection. To reach Gorman, fly the 109-degree radial of the Avenel Vortac until you intercept the 328-degree radial of the Gorman VOR. Then fly direct to Gorman VOR. From this point, proceed according to your flight-planned route, unless otherwise instructed. Notice that Ninty intersection has a minimum crossing altitude of 8,800 feet for the Gorman transition. If you were using the Lake Hughes transition, the minimum crossing altitude for Ninty would be 6,000 feet. These altitudes are necessary to achieve the minimum altitudes along the transition routes. As you have seen, an instrument departure procedure can take many forms and is frequently changed. Because of this, it's important that you understand the procedure and its requirements on you and your aircraft before you take off.
00 Alpha, cleared to Irish intersection. Hold west on Victor 134. 5-mile legs, left turns. Expect further clearance at 1425. Anticipated.
Cessna 4905, Kilo Alpha, Laramie 17,000, Cheyenne 25.
United 327 Heavy, descend and maintain 7,000, cross Henderson VOR at or below 10,000.
Although the departure and arrival phases of instrument flight are often considered the most demanding, the en route segment can test your IFR skills just as easily. You must be able to combine your ability to control your airplane accurately using instrument interpretation with precise navigation skills, so your exact position is never in doubt. The Jeppesen en route charts are designed to simplify instrument navigation. Whether you're following a route you've flown hundreds of times or one in which ATC has just directed you to an intersection to enter a holding pattern. In this program, we'll look closely at the detailed information printed on the en route charts. By understanding the exact meaning of each symbol, you'll be able to rapidly and accurately interpret all the data shown. Let's begin by looking at the low altitude en route charts, which are used for flight below 18,000 feet MSL. Jeppesen prints several low altitude en route charts that cover the United States. There are a number of ways to locate a particular chart or find a specific location or route. For example, on the front panel is a chart index. The heavy black border surrounds the coverage region of the chart in hand. U.S. low 19 and 20 charts provide en route information for part of the central United States. Major cities are shown to further help you with chart selection. Cities shown with bold type and gray shading depict terminal areas which have a published area chart. Time zone boundaries are identified by a series of T's on the chart index. This example shows the division between the mountain and central time zones. The front panel also provides the formulas for converting daylight and standard time to universal coordinated time. Here you can see the conversion formulas for both mountain and central times. Above the chart index is the effective date. You should not use this chart before 0901 Zulu on 11 September. If the chart does not have a specific effective date, it states effective upon receipt. In addition, the front panel contains a listing of major changes which have occurred since the last printing of the chart. On the back panel, you can use a feature called ZigDex, or Zigzag Index, to locate major cities. For example, Goodland is located on panel 6 of the U.S. low 19 chart. To find the city, open the chart to panel 6. The en route charts are designed so you can follow your flight's progress by turning the panels like the pages of a book. This convenient feature helps in cockpit management since it is seldom necessary to completely unfold a chart. Generally, the back panel also contains a listing of special use airspace and, if applicable, part-time terminal airspace hours. These will be discussed later in this program. The bottom portion of the front panel is the City Location Guide. This is an alphabetical list of cities with IFR airports only, and their corresponding locations on the chart. For example, Goodland is located on Panel 6, Section C. When a chart is opened to a particular panel, which in this case is Panel 6, it can be further divided into 4 sections by imaginary horizontal and vertical lines. These sections are labeled in the top and bottom margins as A, B, C, and D. The panels and sections are useful location identifiers. As previously noted in the City Location Guide, Goodland is located on Panel 6, Section C. Now let's move to the chart itself. We'll begin by looking at some basic methods of airspace depiction. Controlled airspace is shown in white. Within controlled airspace, ATC provides separation for IFR traffic. Uncontrolled, or Class G airspace, is shown in gray and extends upward to 14,500 feet MSL. Although high-altitude jet routes pertain to flight at and above 18,000 feet, they are printed on low-altitude charts for orientation. These routes, which are shaded green, help you transition from the low-altitude structure to the high-altitude structure and back again. Special use airspace is shown in green and magenta and is designated for use whenever aircraft activities require airspace operational limitations. For example, a restricted area is outlined with magenta diagonal slashes. The identifier, affected altitudes, times of activity, and controlling agency are shown. If space is limited, this information is printed either adjacent to the area or will be found on the front or back panel in the section entitled Special Use Airspace. This particular restricted area is R4806E. It uses the airspace beginning at 100 feet above the ground and has an unlimited ceiling. The area is active from 0500 to 2000 local time, Monday through Saturday, and other times by NOTAM dissemination. Los Angeles Center is the controlling agency. Green diagonal slashes surround a warning, alert, or MOA airspace. This MOA has a floor of 100 feet AGL and extends up to flight level 180. The ball flag indicates that there is additional information about the area contained elsewhere on the chart. Here it states to contact Nellis Control or the nearest FSS prior to entering the MOA. Now let's look at the types of controlled airspace that are found in terminal areas. An airport surrounded by Class C airspace is enclosed by a shaded blue outline with a series of Cs included. The upper limit of the Class C airspace is shown next to the area. However, some Class C airspace areas have shapes that do not conform to the standard circular dimensions due to their proximity to high terrain or other types of airspace. Class B airspace areas are depicted by a shaded magenta outline with a series of Bs included surrounding the primary airport. This symbol represents the lateral boundary for the upper limit of the Class B airspace. The altitude for the upper limit is shown to help you select an altitude to overfly the airspace. You'll find a detailed portrayal for each sector on the Class B airspace charts that accompany your area charts. The locations of area charts are identified on en route charts by shaded gray dashed lines that surround the charted region. These charts use the same symbology as en route charts, but their scale has been adjusted to provide more detail. You should refer to the area chart if your departure or destination airport is within the boundary shown on the en route chart. The lateral boundaries of the surface area for Class D and Class E airspace are depicted with a blue dashed line. The class of airspace will be indicated within the parentheses along the boundary. An asterisk indicates that the hours of operation are found on the back panel in the section entitled Part-Time Terminal Airspace Hours, Class CDE. In this example, the airspace is Class D. Effective times are 0600 to 2200 local time. The airspace becomes Class E at other times. Surface areas of controlled airspace where special VFR is not permitted are depicted with small magenta dots, such as here at Cleveland Hopkins International Airport. There are many items printed on en route charts to help you maintain orientation. For instance, the green dashed line, which shows 2 degrees east, depicts the magnetic variation for this region. Latitude and longitude lines are shown on the chart by thin green lines, such as 39 degrees north latitude and 91 degrees west longitude. A distance ratio at the top of each chart shows you the scale. In this case, 1 inch equals 15 nautical miles. A nautical mile scale is provided along the top of each chart. Beneath the chart number, it is noted that the Lambert conformal conic projection is used to minimize distortion in transferring a section of the Earth's curved surface onto the flat chart. With this type of projection, a straight line on the chart represents a great circle route, which is the shortest distance between 2 points along the curvature of the Earth. Another item used to help with orientation is the set of wings with a north barb pointing to true north. Light blue bands portray areas where en route charts overlap one another. In this instance, the low 10 and low 11A and 15 represent the exact locations where those charts overlap this chart. This note refers to an area which is covered elsewhere in an inset. If the inset is on a different chart, it will be noted. In this case, the inset provides you with the en route data you need, covering an off-the-chart area over a body of water. Let's continue by looking at airport symbols and related information. Civil VFR airports are identified by small green circles with cogs. Military VFR airports are shown by smooth green circles. Civil IFR airports are shown by small blue circles with cogs. And military IFR airports are shown by smooth blue circles. Both civil and military seaplane bases are charted with an anchor inside the appropriate symbol. Heliports are labeled with an H. Notice again that IFR airports are in blue, and VFR airports are in green. Civil airports have cogs, and military airports are smooth. The airport symbols on en route charts are divided into 2 main categories: those showing airports with a standard instrument approach procedure published by Jeppesen, and those without. When an airport has a standard instrument approach procedure, the airport location is labeled in all capital letters, and the lettering and symbol are in blue. As you might remember, this information is also found on the bottom front panel of the appropriate chart. The approach charts are indexed under this name. The airport's name is also provided when it differs from its location. In this example, Hale County Airport is located in Plainview, Texas. If applicable, frequencies for FSS, ATIS, ASOS, and AWAS are listed above the airport location. Below the airport name is the Jeppesen NAV data, or ICAO airport identifier, along with the airport elevation and the longest runway length to the nearest 100 feet. In this example, by adding 2 zeros, 60 equates to 6,000 feet. Locations of airports without published instrument approaches are indicated with lowercase letters, and the lettering and symbol are in green. These VFR airports also contain an airport identifier, airport elevation, and runway length. An S indicates a soft surface. The absence of an S means it is a hard surface. Jeppesen uses various symbols to show navigation aids. For instance, a VOR is presented as a compass rose with a thin barbed line that orients the symbol to magnetic north. This barbed line allows you to measure the magnetic bearing of any course by using a Jeppesen IFR en route plotter. DME and TACAN facilities are portrayed by serrated circles. Both of these stations provide slant range distance information. In addition, TACAN facilities provide continuous bearing information for suitably equipped aircraft. When a VOR station is combined with a TACAN or DME facility, the resulting VORTAC or VOR DME is shown by combining the 2 symbols. NDBs are marked by a series of 3 concentric green dotted circles with a thin barb pointing to magnetic north. The frequency, identifier, and Morse code for the NDB are listed below the facility name. A localizer facility is shown on the en route charts only if it performs an ATC function, such as identifying a fix, and is noted with a half-feathered arrow. In this case, Kirk is the intersection. The localizer frequency, identifier, Morse code, and the inbound course are shown. Now let's look at the identification and communications data that coincide with the NavAid symbols. When a NavAid is an airway or route component, the identification is given in a shadow box. In this example, the frequency for the Monroe Vortac is 117.2 megahertz. The station's three-letter identifier, MLU, and the Morse code ID are also shown. The D preceding the frequency indicates DME capability, and the L in parentheses represents low-altitude NavAid operational range. The information for a NavAid which is not part of the airway or route structure is not enclosed in a box. For instance, the VOR located at Higginsville Industrial Municipal Airport is used primarily for terminal operations, as depicted by the T in parentheses. The navigation information for a TACAN or DME station which is not frequency paired with a VOR is shown next to the symbol. The frequency of 111.6, shown in parentheses below the TACAN channel, provides civilian reception of distance information. The NavAids at Randolph Air Force Base show a similar situation. Although the VOR and TACAN appear to be co-located, they are actually separate NavAids as shown by the notation. The VOR frequency of 112.3 will not provide distance information. The frequencies for en route radio communications are listed across the top of the NavAid box. If voice capability is not available through the NavAid, only the Vortac navigation frequency is shown. The number shown directly above the box is the frequency available to communicate with the flight service station. Radio frequencies, which are in the 120 megahertz range, are shown with the first two digits omitted. Wichita is the FSS you can contact. A G next to the frequency indicates the flight service station guards or receives on that frequency. They transmit through the Anthony Vortac frequency of 112.9. En route flight advisory service is identified by the WX abbreviation. You can contact Columbia Flight Watch on the designated frequency of 122.0. If a star precedes any frequency, it means that service is not continuous. For example, Flight Watch service normally is provided between 6 a.m. and 10 p.m. local time. Since the purpose of Flight Watch is to gather and distribute current weather information to en route pilots, the Flight Watch specialist will not open, close, or file flight plans. Availability of another type of en route weather service is shown by a HIWAS designator. HIWAS stands for Hazardous In-Flight Weather Advisory Service and is continuously transmitted over the VOR frequency. HIWAS broadcasts contain weather advisories, including severe weather alerts, SIGMETs, AIRMETs, and urgent PIREPs. The letters TWEB signify that transcribed weather broadcasts, or TWEBs, are available through this facility. Selected VORs and NDBs broadcast continuous weather information over the NavAid frequency. TWEBs consist of recorded tapes giving local weather conditions, along with general forecast and route information for the area. Although the information varies, the broadcasts generally contain route-oriented in-flight advisories, winds aloft, current weather reports, NOTAMs, and weather notices. The small encircled dot shows another en route communications service. The Great Falls FSS transmits and receives on 122.45 at the Miller Peak Remote Communications Outlet, or RCO. The black ticked line signifies the boundary between Salt Lake City Center and Seattle Center. You should expect a frequency change near this line. Boxes containing ARTCC frequencies can also be found throughout the charts. The next area we'll look at is how airways and their associated navigation components are shown on en route charts. Victor airways are formed by radials extending from VOR, VORTAC, or VOR DME stations. The airway center line is identified by a solid black line. The VOR radials forming the airway are labeled next to the NavAid symbols. The standard airway width of 8 nautical miles is maintained to a point 51 nautical miles from the NavAid. If the airway extends beyond this point, the controlled airspace expands to include the areas which diverge from the NavAid at angles of 4.5 degrees. Victor airways are identified by a number that indicates their general direction. Even-numbered airways are usually oriented in an east-west direction. Odd-numbered airways are generally oriented north and south. When more than one airway shares a common route segment, all identification numbers are shown. When special information is needed and space is limited, a circled letter, called a ball flag, directs your attention to a note printed on the panel. This ball flag shows that a segment of Victor 55 does not exist when the Devil's Lake East MOA is active. All airway distances are expressed in nautical miles, unless otherwise noted. An enclosed number indicates the total mileage between NavAids. Mileage figures not enclosed, such as 27 and 14, indicate the distance between intersections, VORs, and mileage breakpoints. In this example, the distance from Farmington to DD intersection is 27 miles, and from DD to Cape Girardeau, 14 miles. The total distance from Farmington to Cape Girardeau is 41 nautical miles. Mileage figures not only help you compute your total trip distance, but also assist in determining the changeover point where you should switch from one NavAid to the next. Unless otherwise specified, the changeover point, or COP, occurs halfway between the NavAids. When the changeover point is not at the midpoint, it is shown with this symbol. In this example, the COP is 59 miles from Twin Falls VORTAC and 90 miles from Salt Lake City VORTAC. By changing over at the recommended point, you will continue to receive reliable, accurate NavAid signals. The location of the changeover point can affect the shape and therefore the controlled airspace of an airway. For instance, if an airway is 100 miles long and the COP is located in the middle, then the width of the airway is 4 nautical miles on either side of the center line. By moving the COP closer to one facility, the controlled airspace changes due to the 4.5-degree angle that diverges beyond 51 nautical miles from the NavAid. A mileage break symbol is most often associated with a course change where an intersection is not designated. Where a mileage break has been unnamed, Jeppesen has assigned a nav data database identifier. Since these identifiers apply only to the Jeppesen database, the identifier should not be used as a reporting point for ATC or when filing a flight plan. An arrow along an airway points from the NavAid designating a reporting point. In this example, Toddy intersection is defined by the 167-degree radial from Hugo VORTAC and the 081-degree radial from Pueblo VORTAC. When the radial that defines a fix is not designated as a flyable route, it is indicated by a long, thin arrow. Orway is defined by the intersection of the 133-degree radial of Colorado Springs, and the radial which defines Victor 10, 244. Where distance measuring equipment can be used to define a fix, a D with a solid arrow is shown with the mileage being determined by that listed along the airway. In this case, the DME distance from Pueblo Vortac to Orway intersection is 18 nautical miles. If there is more than one fix along the airway, the mileage immediately follows the D. Here, the distance to Toddy is 38 nautical miles. Unless you're in radar contact, IFR position reports are required at certain points along the airway. These points are referred to as compulsory reporting points and are indicated by solid triangles. If the compulsory reporting point is at a navigation facility, the solid triangle will be part of the facility symbol. Open triangles depict non-compulsory reporting points requiring a position report only when requested by ATC. Intersections are associated with reporting points and provide a positive means of establishing your position. The name of the intersection is usually 5 letters and is shown near the fix. In the case of Hardy intersection, note that the holding pattern includes a speed restriction. In some situations, the nav aid forming an intersection is located off the chart or at a considerable distance from the intersection. In other cases, the thin arrow identifying the fix might be hidden by other information. When this happens, the 3-letter identifier, radial or bearing, frequency, and distance, if appropriate, are shown along with a portion of the intersection identifier arrow. Where the nav aid forming an airway is located off the chart, its name is shown along the edge. When the nav aid helps form an intersection along the airway, or the changeover point occurs on the chart you're using, the nav aid's frequency and identifier are also shown. For example, Wormy intersection can be identified by the 30 DME from Llano Vortac along the 110-degree radial. Now let's review the various en route altitudes. Each designated airway in the continental United States is charted with a minimum en route altitude, or MEA, that has been established for 2 primary reasons. First, it guarantees obstacle clearance, and second, it indicates the lowest altitude at which you can expect adequate navigation signal reception. In addition, you can usually expect adequate communications at the MEA, although it is not guaranteed. When you're on an airway, the MEA normally provides a minimum of 1,000 feet obstacle clearance over non-mountainous terrain and 2,000 feet in mountainous areas. The minimum en route altitude is shown below the airway identifier. On some airways, the MEA is different depending on the direction you're flying. For example, if you're flying west from Stano intersection, the MEA is 12,000 feet. However, if you're flying eastbound from Flood, the MEA is only 9,000 feet. Although you can typically expect navigation signal reception at the minimum en route altitude, a broken bar symbol indicates a possible gap in the navigation signal even if you maintain the MEA. This break usually occurs for only a very short distance. When the MEA changes at a location other than a nav aid, a break in the airway is shown, and small bars are placed across the airway centerline. Notice that the MEA is 4,300 feet to the west of Safer intersection and 3,400 feet to the east. When rising terrain requires that you climb to a higher altitude before reaching a fix, a minimum crossing altitude, or MCA, is established. The MCA is shown by an information grouping consisting of the Victor airway number, the crossing altitude, and the direction of flight. When a minimum crossing altitude occurs at a nav aid, it is identified with a numbered ball flag. The applicable information is listed elsewhere on the same panel. In addition to an MEA, some route segments also provide a minimum obstruction clearance altitude, or MOCA. The letter T for terrain is shown with the MOCA to distinguish it from the other types of altitudes. The MOCA meets obstacle clearance requirements but only provides reliable signal reception when you're within 22 nautical miles of the navigational facility. In a few cases, maximum authorized altitudes, or MAAs, are specified. These normally occur below special use airspace or when two VORs transmitting on the same frequency could cause signal interference at higher altitudes. They are indicated by the letters MAA, followed by the applicable altitude. At some intersections or fixes, terrain can interfere with the reception of the nav aid which forms the fix. Where an altitude higher than the MEA is required to identify the fix, a minimum reception altitude, or MRA, is designated. The next area we'll cover is the high-altitude charts, and some of the items which appear differently on them. Since these charts cover portions of the Canadian and Mexican high-altitude structure, information about airspace variations is provided on the front panel. A primary difference between high and low-altitude charts is that nav aid information is presented in a different form. For instance, the compass rose that usually surrounds VOR stations is not shown. However, the magnetic north barb is printed for use with the Jeppesen IFR en route plotter. As with low-altitude charts, a shadow box is used to identify a nav aid that is part of the en route structure. However, the shadow is only on the right side of the box since the geographic coordinates for the nav aid are listed below the box. Off-airway nav aids are indicated by omitting the shadow from the frequency box. Frequencies for HIWAS and TWEEB, along with flight watch information, are included on high-altitude charts where available. Jet routes are shown in the same basic manner as Victor Airways. If the jet route designator is shown inside an arrow, such as J110, the airway is a preferred one-way route. If an effective time is also included, it is only one way during that particular time. Otherwise, it is a two-way airway. MEAs are only shown on high-altitude charts when they are higher than 18,000 feet. Sometimes a nav aid or intersection appears to be part of a jet route, when in fact the route bypasses the fix. The letter D designates a preferred IFR direct route which is not part of the jet route system and is 130 nautical miles or more in length. On high and low altitude en route and area charts, Jeppesen also provides minimum off-route altitudes, or MORAs, located within grids formed by lines of latitude and longitude. In this example, the number 26 represents a grid MORA of 2,600 feet and is an altitude which will provide obstacle clearance during an emergency descent. If the highest natural or man-made object within the grid is a non-mountainous area, the minimum off-route altitude provides you with at least 1,000 feet of clearance. When the highest object or terrain is in a mountainous area, 2,000 feet of clearance is provided. Additionally, for terrain awareness, generalized terrain contours are depicted on selected area charts. Within contour intervals, some, but not all terrain high points may be included along with their elevation above mean sea level for use as additional reference. DME arcs are shown for situational awareness. On high-altitude charts, the lines of latitude and longitude, as well as the magnetic variation, run through the entire chart. Flight in the instrument environment challenges your piloting skills continuously. Jeppesen en route charts provide the navigation and communication data needed to meet the challenge. However, their effectiveness depends on your correct interpretation of the information portrayed.
To provide accurate IFR navigation, en route and area charts are published depicting IFR routes, radio facilities, radio frequencies, en route altitudes, and various other information. It's essential that you be able to extract needed information rapidly and accurately from these charts. En route charts are produced in two groups. The first is for use in the high altitude structure. The second is for use at lower altitudes, up to, but not including, 18,000 feet. During this program, we'll look at the information on these low altitude charts, since they will probably be the first en route charts you will use during your instrument training. The National Ocean Service, NOS, prints 28 low altitude charts covering the United States. An index panel on the front shows the area covered by each chart. This panel aids you in selecting the charts needed for a specific flight. Major cities are shown to further aid you in your chart selection. Cities in black depict terminal areas for which an area chart is published. The bold lines indicate the chart in hand. On the chart index, time zone boundaries are indicated by dotted lines. The standard time zones are indicated at the top of the chart. A legend describing the meanings of the symbols is printed on the inside of most charts. Each chart contains 5 colors. Brown is used to show low and medium frequency aids and route data. Airports without a published instrument approach, military training routes, and the borders to military operation areas. Brown is also used to depict areas of Class G airspace, which extend from the surface up to 14,500 feet. Within the conterminous U.S., all airspace above 14,500 feet is controlled. The white areas on the chart represent areas of Class E airspace, unless otherwise indicated. Blue is used for air defense identification zones, as well as prohibited, restricted, alert, and warning areas. In addition, blue depicts Class C airspace. Class B airspace, Air Route Traffic Control Center boundaries, as well as ARTCC remote sites. Airports shown in blue have an approved instrument approach procedure published in both the Department of Defense and the NOS Flight Information publications. Airports with instrument approaches, which only appear in the NOS Flight Information publication, are shown in green. Green also is used to depict shoreline, time zones, and isogonic lines. The majority of black print is used for VHF and UHF route data, such as VOR nav aids, communication and frequency boxes associated with the navigational facilities, and airways. VOR facilities on the chart are indicated by a hexagon symbol, normally enclosed in a compass rose, oriented to magnetic north. A TACAN facility operates in the UHF frequency band to provide azimuth and distance information for military aircraft. When a VOR and TACAN facility are co-located, the resulting facility is called a VORTAC. A VORTAC is shown on en route charts with the extensions of the TACAN symbol filled in. Properly equipped civil aircraft can use the VOR portion of a VORTAC for course guidance and the TACAN part for distance information. This is accomplished through frequency pairing, which means that when you select the VOR frequency, the UHF frequency of the TACAN is automatically selected by the DME equipment in your aircraft. To civilian aircraft, a VOR DME nav aid works like a Vortac station. When you select the proper VOR frequency, your DME is automatically paired to the correct UHF frequency. The information boxes associated with nav aids provide the name of the facility, the frequency on which the nav aid transmits, the identification letters, if available, the channel number used by the military for DME, the Morse code, which corresponds to the facility's identification letters, and the geographic coordinates for that facility. Flight Service Station communications frequencies available at a nav aid are listed across the top of the information box. The letter R indicates that the facility only receives on that frequency. If it's followed by a T, it means the frequency is only used for transmissions. When the FSS has a remote antenna at the site, the name of the controlling facility is added. Shadow boxes indicate the standard Flight Service Station frequencies are available in addition to those listed above the box. FSS standard frequencies include 121.5 and 122.2. A solid square in the upper left portion of the box means that hazardous in-flight weather information is available from HIWAS. A white T in a black circle indicates that the facility has transcribed weather broadcasts. If a line appears under the frequency, the nav aid has no voice capability. An overprint on the frequency indicates some type of abnormal status, and you should check the NOTAMs. In this case, the NOTAM indicates the VOR may be shut down. VHF navigation routes, which are defined by VORs, are designated as Victor airways in the low-altitude structure. In this example, the airway running southeast of Farmington is designated Victor 178. In order to fly outbound from Farmington on this portion of the airway, you must maintain a magnetic course of 129 degrees. Victor airways are normally 8 nautical miles wide. This width is maintained to a point 51 nautical miles from the nav aid. If the airway extends beyond this point, the controlled airspace includes the areas on either side of the center line, which diverge from the nav aid at angles of 4.5 degrees. All mileage listed on en route charts are nautical miles, unless otherwise noted. The total mileage between compulsory reporting points and radio facilities is enclosed in a box. Mileage figures not enclosed in a box, such as 27 and 14, indicate the distance between reporting points, radio aids, and/or mileage breakdowns. In this example, the distance from Farmington to Dede intersection is 27 miles, and from Dede to Cape Girardeau, 14 miles. The total distance from Farmington to Cape Girardeau is 41 nautical miles. A mileage breakdown is identified by a small x and is normally associated with a course change where a reporting point has not been established. When flying between two nav aids, you normally change the frequency halfway between the two stations. For example, if you were flying from Tar River to Cofield, you would change to Cofield 23.5 miles from Tar River. In some areas, however, the actual point of change will be designated. In this case, the mileage from the corresponding nav aids is indicated with the changeover symbol. The facilities used to define a fix are indicated by arrows. In this example, Yummy intersection is defined by the 248-degree radial from Glade Spring VOR DME and the 295-degree radial from the Holston Mountain Vortac. At locations other than where two airways intersect, A thinner arrow defines the fix. Here, TRIP's intersection is defined by the 041 degree radial of Falmouth and Victor 128. Where distance measuring equipment can be used to define a fix, an arrow with an open head is shown, with the mileage being determined by that listed along the airway. In this case, the DME distance to Calif intersection is 19 nautical miles. If there is more than one fix along the airway, the mileage to the fix from the nav aid is enclosed in a D-shaped box with the arrow attached. Here, the distance to trips is 30 nautical miles. Unless you are in radar contact, IFR position reports are required at certain points along the airway. These points are referred to as compulsory reporting points and are indicated by solid triangles. If the compulsory reporting point is at a navigation facility, the solid triangle will be a part of the facility symbol. Open triangles depict non-compulsory reporting points requiring a position report only when requested by ATC. On IFR flights, position reports are normally made by direct communications with the appropriate air route traffic control center. The division between centers is designated by a patterned line. The names of the controlling centers appear on their respective sides of the dividing line. To provide direct communications throughout their area, ARTCCs operate remote radio sites. The location of each site is indicated by a blue patterned box containing the name of the controlling center, the remote site name, and the frequencies used for contacting the center when you're in that general area. Terminal airspace areas that require communications are indicated on NOS en route charts. For example, Class B and Class C airspace areas are depicted by blue shading around the primary airport. A solid border indicates Class B airspace. The white and blue cross-hatchings surrounding Class B airspace areas depict the 30 nautical mile Mode C veil. If the blue shading is enclosed with a broken border, it is a Class C area. The border represents the general size and shape of the upper portions of the associated controlled airspace. Airports surrounded by Class D airspace will have a D inside a box after the name. Likewise, the primary airport of a Class C airspace area is depicted with a C. If the airspace is part-time, a star appears after the box. Information about the hours of operations can be found in the voice communication table, which is usually located on a chart panel near the legend. Areas in which fixed-wing special VFR flights are prohibited are indicated by the notation "No SVFR" above the airport name. As mentioned before, airports without an instrument approach are shown in brown, and airports with a published approach are depicted in either blue or green. With all airports, the airport elevation, availability of night lighting, and the length of the longest runway in hundreds of feet are noted on the chart. If an A appears with the name, ATIS information is available on the frequency shown. For terminal communications, such as tower, approach and departure control, and clearance delivery, you will need to refer to the air-to-ground voice communications panel. Non-directional beacons are low or medium frequency nav aids generally associated with instrument approaches. The location of an NDB is marked by a series of concentric brown dotted circles. Information pertaining to the facility name, frequency, and identifier are located near the symbol. An Instrument Landing System, or ILS, localizer course is depicted by feathered arrows when it performs an ATC function. The ILS frequency, identifier, and Morse code, along with the inbound course, are shown. Now, let's discuss the various altitudes shown on the chart. Minimum en route altitude, abbreviated MEA, is the lowest altitude between radio fixes, which meets obstacle clearance requirements and assures acceptable navigation reception. In addition, you can usually expect adequate communication at the MEA, although it is not guaranteed. This altitude is listed along the airway or route segment to which it applies. On some airways, the MEA is different, depending on the direction you're flying. For example, if you're flying west from Stano intersection, the MEA is 12,000 feet. However, if you're flying eastbound from Flood, the MEA is only 9,000 feet. A minimum obstruction clearance altitude, or MOCA, meets obstruction clearance requirements, but only guarantees reliable signal reception when you're within 22 nautical miles of the navigational facility. This altitude is listed when it is lower than the MEA. To avoid confusion, the MOCA is preceded by an asterisk. To indicate that a change in MEA or MOCA occurs on a route segment at other than a navigation facility, a break in the airway is shown, and small bars are placed across the airway center line. When the point is not a designated intersection or nav aid, the mileage breakdown symbol is used. Here, the MEA changes between the United States and Canada. At some intersections or fixes, terrain can interfere with the reception of the nav aid, which forms the fix. Where an altitude higher than the MEA is required to identify the fix, a minimum reception altitude, or MRA, is designated. A flag with an R is attached to the fix to indicate an MRA. The altitude is listed near the name of the intersection. In this case, you must be at 13,000 feet in order to identify window intersection. A minimum crossing altitude, abbreviated MCA, is designated whenever intervening obstacles prevent you from maintaining obstruction clearance during a climb to a higher MEA. The MCA is shown by an information grouping consisting of the Victor airway number, the crossing altitude, and the direction of flight. A flag with an X is placed at the fix where the MCA applies. In a few cases, maximum authorized altitudes, MAAs, are specified. These normally occur below special use airspace or because two VORs transmitting on the same frequency cause signal interference. They are indicated by the letters MAA, followed by the applicable altitude. Certain areas are designated special use airspace due to hazards or special activities that occur within them. Depending on the flight restrictions or activity, they are labeled as prohibited, restricted, warning, alert, or military operations areas. Each area has a designation number, and information on the restrictions can be found on the front panel of the chart. Military operations areas, which are depicted in brown, each have a designated name. Additional information about the area can be found on the front panel of the chart in a separate table. The isogonic lines, which are depicted in green, run through the entire chart. The amount of magnetic variation is depicted near the edges of the chart. Since all radio navigation radials and bearings are magnetic, this information is useful to you when you need to determine a true course. On en route charts, the location of an area chart is depicted by dashed lines. These charts provide blow-ups of certain major terminal areas, making it easier to read the navigational information. Area charts use the same symbology as en route charts. NOS publishes 12 area charts, covering some of the major terminal areas in the United States. All of the area charts are found on one two-sided sheet. En route and area charts contain a vast amount of essential data. Since chart space is limited, much of the information is coded, to minimize clutter and conserve space. As you become more familiar with the format, you'll find that you can locate the necessary information easily.
Throughout most of your IFR flights, you are usually followed by some segment of the air traffic control system. On many cross countries, your flight will be handed off from departure control to an air route traffic control center. This handoff is usually accompanied by instructions which include the name of the next facility, the frequency, and any other pertinent information.
Cessna 241, contact Los Angeles Center on 127.1 at Leste intersection.
Cessna 241, Los Angeles Center on 127.1 at Leste.
After you have established communications and have been radar identified by the next controller, you can expect normal radar services until the controller informs you that radar service has been terminated or radar contact lost. While in radar contact, there are certain reports listed in the Airman's Information Manual which you should make to ATC. For example, you should let ATC know when you are leaving an assigned altitude for a newly assigned altitude, and any time you're changing altitudes when VFR on top. Other reports include a change in the average true airspeed of 5% or 10 knots, whichever is greater. You should also notify ATC if you cannot maintain a climb or descent of at least 500 feet per minute. Other reports include the time and altitude when you reach a holding fix or point to which you have been cleared, leaving an assigned holding fix or point, and initiating a missed approach. In addition to the reports listed in the AIM, regulations require you to report any navigational approach or communications equipment malfunction while in flight. You are also required by regulation to report any unforecast weather encountered and any other information relating to the safety of flight to an ATC facility. There are other reports which you need to make when not in radar contact. For example, you should report a new estimated time of arrival if it changes by more than 3 minutes. You should also report the final approach fix inbound on a non-precision approach, or the outer marker, or the fix used in lieu of it on a precision approach. In order for ATC to follow your progress and keep you separated from other traffic in a non-radar environment, regulations require that you supply position reports. On an en route chart, a compulsory reporting point is indicated by a solid triangle like the one at Pulaski VOR. A report at a non-compulsory fix, such as Doyley intersection, is only required when it is requested by ATC. The IFR position report that is required over these points should include your identification, position, time, flight altitude, the name and ETA over the next reporting point, and the name of the following reporting point. Even if you're in radar contact, you should always keep track of your flight's progress, because you never know when radar contact may be lost or terminated, and you'll have to start making position reports. To make sure you are flying on your assigned altitude when below 18,000 feet MSL, adjust your altimeter to the current setting reported by a station within 100 nautical miles. At or above 18,000 feet, set the altimeter to 29.92. Your altitude is now read as a flight level. For example, 31,000 feet is flight level 310. When you're flying IFR in uncontrolled airspace, you should use the hemispheric cruising altitudes. Below 18,000 feet MSL, use even 1,000-foot altitudes for westbound flights and odd 1,000-foot altitudes for eastbound flights. Although the altitude for your flight in controlled airspace is assigned by ATC, it often follows these cruising altitudes. At or above 18,000 feet, you will be assigned even or odd flight levels. As you're approaching your destination, ATC will issue you a descent clearance.
Cessna 241, descend and maintain 10,000.
This clearance gets you to an altitude where you can begin the approach procedure. There are times when your flight must be delayed for reasons such as traffic separation or approach sequencing. In these cases, ATC issues you a holding clearance and has you enter a holding pattern. If the holding pattern is charted, the clearance contains the direction from the fix, the name of the fix, an instruction to hold as published, and an expect further clearance time.
Cessna 52241, hold northeast of Matin intersection as published. Expect further clearance at 1533.
If there is no published holding procedure, ATC issues a more descriptive instruction. All the items in the previous clearance are given except for hold as published. Instead of this phrase, you receive a description of the course line you're to hold on, the length of the legs if appropriate, and the direction of the turn if you're to use a non-standard holding pattern. While in a standard holding pattern, all turns should be made to the right. These turns should be limited to a standard rate or 30 degrees, whichever is less. Non-standard patterns use the same procedures. However, now you make the turns to the left. To help you understand this procedure, let's look at some of the parts of a holding pattern. The inbound leg takes place along the holding course. When you reach the fix, turn to the outbound leg. After the proper time or distance, turn to re-intercept the inbound leg. The side of the course where the holding takes place is referred to as the holding side. Unless specifically stated in your clearance, the length of each holding leg is determined by time. The timing of each inbound leg is 1 minute when you're holding at or below 14,000 feet, and 1.5 minutes when holding above 14,000 feet. For simplicity, let's use 1-minute legs for the rest of the discussion. In a no-wind condition, the inbound and outbound legs will take the same amount of time. Since a no-wind condition is rare, you need to make adjustments on the outbound leg to achieve the proper inbound timing. For example, suppose on your initial timing it took you 1 minute 15 seconds to fly inbound. To correct this situation, you should try flying outbound for 45 seconds before turning inbound. This should now make your inbound leg approximately 1 minute in length. A crosswind also requires an adjustment. However, if you use the same amount of correction on the outbound leg, you will overshoot the course following your turn inbound. To compensate, you must triple the correction you used on the inbound course and apply it to the outbound heading. This should place you near your inbound course when you complete the turn. With some exceptions, the holding speed for propeller and jet aircraft is 200 knots indicated airspeed, up to 6,000 feet MSL. Above 6,000 feet to 14,000 feet, the maximum holding speed is 230 knots. And above 14,000 feet, the maximum holding speed is 265 knots. In some cases, holding speed may be restricted to 175 knots or 210 knots indicated airspeed. When this is the case, you will see an icon or note on the chart depicting that holding speed. If the indicated airspeed of your airplane exceeds the maximum holding speed, you should reduce it at least 3 minutes before your ETA at the holding fix. To minimize the amount of maneuvering you have to do, the FAA recommends that you enter a holding pattern by one of three methods. Use of these procedures makes the entry simpler and reduces the possibility of penetrating unprotected airspace. The area around a holding fix is divided into sectors, which are formed by an extension of the inbound holding course and a line which crosses the course at an angle of 70 degrees, as measured from the inbound course on the holding side. This line, along with the extended holding course, forms two 70-degree sectors and two 110-degree sectors. The two sectors that border the holding course are combined to form a 180-degree sector. If you're approaching from the 180-degree sector and you're entering a standard holding pattern, a direct entry is suggested. This means that after crossing the fix, simply turn right to the outbound heading. When approaching from within the 110-degree sector, a parallel entry is appropriate. As you cross the fix, turn to the outbound heading and parallel the inbound course on the non-holding side. After 1 minute, turn left and return to the holding fix or intercept the inbound course. Use a teardrop entry if you're entering the holding pattern within the remaining 70-degree sector. In this case, after crossing the fix, turn to a heading 30 degrees to the holding course on the holding side. After the appropriate time, turn back to intercept the holding course. When you're cleared into a holding pattern, the easiest method of determining the proper entry is to use your heading indicator and mentally visualize in which sector the inbound holding course falls. To do this, assume the holding fix is in the middle of the heading indicator. Then mentally extend a line from the fix to the top of the instrument, and another line from 70 degrees right to 110 degrees left. These lines now form the teardrop, direct and parallel sectors. In this way, you can quickly visualize the type of entry you should use. For example, if the inbound holding course of a standard holding pattern is generally behind you as you arrive at the fix, you will probably use the direct entry. If the holding course is generally ahead and to your left, use the parallel entry. When the holding course is ahead and to the right, the teardrop entry is normally recommended. The same procedure can be used for a non-standard pattern. However, in this case, use left turns and reverse the parallel and teardrop entries. When leaving the holding fix, you should report it to ATC.
As an instrument-rated pilot, you will have easier access to large airports you might not venture into under visual flight rules. These busy airports require procedures for sequencing aircraft to an instrument approach. Arrival charts provide a smooth transition from the en route structure to busy terminal areas. They simplify arrival procedure instructions and let you and the controllers know what to expect. Standard terminal arrival routes, or STARS, use similar charting conventions as departure procedures. Unlike departure procedures, which help you navigate from an airport to the en route structure, STARS take you from the en route structure down to the vicinity of an airport. They terminate at a fix or nav aid from which you can begin an instrument approach procedure, or at a position where ATC can vector you for an approach. STARS normally contain both a textual description of all transitions plus the arrival route, and a graphic depiction of the procedure that follows normal conventions for terminal charts. STARS are usually filed in front of the primary airport for a specific city. On other airports that use the same stars, a note on the airport chart refers you to the primary airport under which the star is filed. However, in many cases, additional copies of the star are filed in front of other major airports it serves, with minor modifications to emphasize the procedures for that specific airport. Let's look at the Lemig 1 arrival for San Antonio, Texas. This arrival, like most stars, consists of multiple transition routes and an arrival route. This particular arrival utilizes radar vectors to the final approach course. You can distinguish the arrival route from the transitions by the solid route line. You will also notice that the star is named for the fix at which the arrival route begins. In addition to San Antonio International Airport, the Lemig 1 arrival also serves Stinson Municipal Airport. Notice that the chart provides the direct distance from LK intersection, where radar vectors begin, to the airport served. Kelly Air Force Base and Randolph Air Force Base are served by other versions of this star that are included in military subscriptions. The Lemig 1 arrival also contains information that will help jet pilots plan their descents. The vertical navigation planning section on some stars may contain several altitude step-down fixes. Because of the large geographic area covered by standard terminal arrival routes, many of these charts are not drawn to scale. When you file for a star on your flight plan, use an appropriate code just as you do for a departure procedure. For example, the code for the Corpus Christi transition of the Lemig 1 arrival would be CRP.LEMIG1. Notice that the transition portion of the code is listed first for a star, but last on a departure procedure. Whenever a major revision occurs to a star, the number is changed. The next revision for this star will be the Lemig 2 arrival. Standard terminal arrival routes expedite your descent from the en route structure and position your aircraft at a point where you can begin an approach. Unless you indicate no star on your flight plan, ATC can assign one anytime they need to. Being familiar with these procedures will enable you to fly IFR into the most congested airspace with confidence. As an instrument-rated pilot, you will have easier access to large airports you might not venture into under visual flight rules. These busy airports require procedures for sequencing aircraft to an instrument approach. Arrival charts provide a smooth transition from the en route structure to busy terminal areas. They simplify arrival procedure instructions and let you and the controllers know what to expect. Standard terminal arrival routes, or stars, use similar charting conventions as departure procedures. Unlike departure procedures, which help you navigate from an airport to the en route structure, stars take you from the en route structure down to the vicinity of an airport. They terminate at a fix or nav aid from which you can begin an instrument approach procedure, or at a position where ATC can vector you for an approach. Stars normally contain both a graphic depiction of the procedure that follows normal conventions for terminal charts and a textual description of all transitions, plus the arrival route. Stars are published in the corresponding terminal procedures booklet, but unlike DPs, they are filed alphabetically by procedure name near the front of each booklet. You can use the index for determining what stars are available for a particular city or airport. Let's look at the Lemig 1 arrival for San Antonio, Texas. This arrival, like most stars, consists of multiple transition routes and an arrival route. This particular arrival utilizes radar vectors to the final approach course. You can distinguish the arrival route from the transitions by the bold route line. You will also notice that the star is named for the fix at which the arrival route begins. In addition to San Antonio International Airport, the Lemig 1 arrival also serves Stinson Municipal Airport, Kelly Air Force Base, and Randolph Air Force Base. You will find this star listed under each of these airports in the index. The Lemig 1 arrival also contains information that will help jet pilots plan their descents. The vertical navigation planning section on some stars may contain several altitude step-down fixes. Because of the large geographic area covered by standard terminal arrival routes, the charts are normally not drawn to scale. When you file for a star on your flight plan, use an appropriate code just as you do for a departure procedure. For example, the code for the Corpus Christi transition of the Lemig 1 arrival would be CRP.LEMIG1. Notice that the transition portion of the code is listed first for a star, but last on a departure procedure. Whenever a major revision occurs to a star, the number is changed. The next revision for this star will be Lemig 2 arrival. Standard terminal arrival routes expedite your descent from the en route structure and position your aircraft at a point where you can begin an approach. Unless you indicate no star on your flight plan, ATC can assign one anytime they need to. Being familiar with these procedures will enable you to fly IFR into the most congested airspace with confidence. As traffic around an airport becomes more congested, procedures for sequencing aircraft to an instrument approach become necessary. One of the easiest ways for ATC to ensure an orderly flow of traffic is to assign an inbound aircraft a standard terminal arrival route, or STAR. It is important to follow arrival procedures carefully. With that in mind, let's look at a star for a flight into Phoenix Sky Harbor International Airport. As you're approaching Blythe VOR at 12,000 feet, Los Angeles Center issues the following clearance.
Cessna 241, cleared to Phoenix Sky Harbor Airport via the Blythe 2 arrival. Maintain 12000, contact Phoenix approach at Salome on 120.7.
ATC can assign you a star even though you have not requested the procedure, unless you have indicated no star on your flight plan. If you accept the clearance, you must have the charted procedure or at least an approved textual description of the star. Let's review the Blythe 2 arrival. This star begins at the Blythe VOR. From there, you'll follow the 082-degree radial to Salome intersection. Then you'll proceed inbound on the 285-degree radial of the Gila Bend VOR to Saddle intersection. When you reach Saddle intersection, you'll turn east and proceed inbound on the 256-degree radial of the Willie VOR. From over Arlen, you can expect radar vectors to the final approach course if runway 8 is in use. If runway 26 is being used, you should expect radar vectors prior to reaching Tukey intersection. Now that you've reviewed the arrival procedure and set the radios and navigation equipment, you can begin to plan for the approach. Tune in and listen to the ATIS broadcast to get the current weather and information about the approaches in use and the landing runways.
Wind 070 at 8, altimeter 299er2. ILS runway 8 right approach in use, landing runway 8 right. Advise Phoenix Approach Control you have information Romeo.
With this information, you can now review the specific approach chart and determine the frequencies, inbound course, descent and landing minimums, missed approach point, and the missed approach procedure. It's important to review these early in the arrival to reduce your workload later. Just before you reach Hyder intersection, Phoenix Approach issues the following clearance.
Cessna 241 cross Paint intersection at 10,000.
This clearance authorizes you to begin the descent to 10,000 feet at your discretion, as long as you are at 10,000 feet when you pass Paint intersection. To comply with the crossing restriction, you must determine when to start the descent. Since your present altitude is 12,000, you'll need to lose 2,000 feet. Assuming a 500 foot per minute rate of descent, it will take 4 minutes to reach 10,000 feet. A 4-minute descent at a ground speed of 120 knots will cover 8 nautical miles. The distance from Hyder intersection to Paint intersection is 11 nautical miles. Therefore, if you begin your descent after you pass Hyder, you should be at 10,000 feet, approximately 3 miles before Paint. From Paint, it's another 8 nautical miles to Arlen, where you can expect radar vectors off the arrival to begin your approach. A descend via clearance simply instructs you to follow the altitudes published on the star. If you were instructed to descend via the Blythe 2 arrival, you would be expected to stay above the MEAs published on this chart. If ATC amends your route or altitude to something different than what is published on the star, it effectively cancels the procedure and places you on radar vectors. Arrival procedures make the transition from en route to approach an easy and orderly procedure for both you and ATC.